Hola. Hello. Hello, everybody. Hello. Hello and welcome. Hello. Please take a seat. Thank you. Mobile phones, sound off, please. Thank you. I'm going to do it with mine because I forgot. That is great. Thank you so much for coming today. Are we online? Are we online? Are we online? ¿Estamos conectados? Sí, are we online? Okay, thank you. Welcome to this summit, the Web TECNALIA. We're going to talk about some very interesting things. First of all, I would like to introduce our CEO, Jesus Valero. He's going to give us a little speech of welcome and give the background and the setting for the whole day. Please put your hands together to welcome Mr. Valero.
Thank you very much, Irene. So, good morning, everyone. It's a pleasure to be here today and to open this session. In 1495, Leonardo da Vinci was selected to decorate the refectorium of the convent of the Santa Maria della Grazie in Milano, probably you know, where he painted the Last Supper. It was supposed to be an easy task. He was the greatest painter in Italy at this moment. The Last Supper is a very well-known scene, painted many times before. But Leonardo was not interested in painting the expected. So he decided to create the unexpected. And he made 3 different innovations at the same time in this painting of the Last Supper. The first innovation that he made was a technical innovation. He changed the way frescoes were painted because he didn't like too much painting frescoes because it's a difficult technique because you have to paint very fast because frescoes dry very quickly. So he decided to make an innovation, and instead of painting directly a fresco, he mixed a fresco with a tempera, trying to have the capacity of controlling the painting. The second innovation that he made was a completely different innovation that is related to the perspective. He wanted the people coming into the refectory, entering the room, to see the painting of the Last Supper and feeling that the perspective was everything directed to the viewer. And the third innovation that he created in this incredible painting was an innovation that was related not to the perspective, not to the chemistry, but to a completely different thing. It's how to treat the psychological traits of the participants in the painting, how to create movement, how to create the vision that these people that were painted there had feelings, had thoughts, were transmitting something. It was the first time that somebody did that. And he created something absolutely unexpected at the moment. In fact, the moment he finished this painting, the Renaissance started. So he changed completely the world at this moment, and all the painters of Italy came just to see this painting, and was influencing all the paintings in the 16th century in Italy. So he creates something absolutely new. Quantum has also the ingredients to change the world, as Leonardo did with the Last Supper. This is the reason we are here today. But today is a meeting to look ahead, to do like Leonardo did, and this is the reason why we have brought brought all together here to talk about quantum computing. But more important than to talk about quantum computing is to explore how this technology can change the world, and especially can change the industry. For years, quantum has been living in the realm of promise, and today it is starting to move into the realm of possibility, the realm of impact. We have designed this meeting around 3 different key principles that we consider essential for quantum today: honesty, practicality, and results. Because quantum needs less mystery and more clarity, less futurism and more impact, fewer abstract expectations, and more concrete applications. And that is exactly what we will see today in this meeting. At TECNALIA, we have chosen to move forward on this journey alongside an exceptional partner, which is the Wave, a global pioneer in commercial quantum computing based on the quantum annealing. Sorry. Together, we aim to accelerate the industrial adoption of these technologies and demonstrate the quantum is not a distant horizon, but a driving force already beginning to affect many things. Allow me to share something more personal, a little bit more personal right now. A year ago, I was appointed as president of EARTO, the European Association of Research and Technology Organizations, with more than 300 research organizations all over the world and more than 200,000 researchers. And from this EARTO perspective, I can say that here in the Basque Country, we know that we are playing at the forefront of quantum in Europe. Here in the Basque Country, we have industry, we have technological centers, TECNALIA, obviously, universities, startups. We have all these things, but above all, what we have is a culture of collaboration that enables us to turn science into practical things, into industry, into economical value. That is the mission of EARTO, and in a way that is also the mission of TECNALIA. So today's session is a little bit a journey to the future. We will hear from international experts who will present the capabilities of the new Advantage 2, the latest quantum processor from D-Wave. We will explore the European vision for building a competitive quantum ecosystem. We will discover the vast quantum ecosystem, dive into algorithms, metrics, and many other things, real case uses, and so on. And we will give voice to startups that are pushing the boundaries of quantum technologies. So today we are not here just to learn something. We are here to imagine, we are here to question, to discover, to understand what is already viable today and what opportunities are opening right now. We are here to do the same that Leonardo did at the end of the 15th century. I would like to thank you for your presence here today with us, but also for your curiosity. The summit is designed for those of you who have the responsibility and the opportunity to anticipate the future. So I encourage you to listen carefully, to ask questions, and to let yourselves be inspired today. Thank you very much, and I hope you will enjoy this transformative session.
Thank you, Jesus. Welcome again. Today's going to be a really, really interesting day, and we hope a great day. And I want to thank every single person in this room and the people online. But I also want to thank the team from D-Wave for coming all the way from their homes to be here with us. We have 3 members of the team. And I also want to thank the people in our team here in TECNALIA that has made this possible. And I want to thank someone that is not here today, but I hope is online. It's our colleague, Esther Villar. She should be here, and this is also her achievement. So hi, Esther, if you are watching from home, and hello to everybody that is at home today. We expect to make this day a very interesting day for you too. There is something that we should be all sharing at the end of the day, is that quantum is not just a technology, it's a new way of thinking, and it's a new way of looking at problems. And we hope that we show you the way today, at least with some practical examples and some really interesting people. We wanted to make today a day of the wide perspective. We wanted to have some people talking about the ecosystem and the things that are happening at the wider picture at the European and regional level, and what type of efforts are being made from different parts of the ecosystem. We wanted to bring you here top minds working on this technology, so expect some very technical presentations, and we hope you follow. We wanted to bring you here use cases from industry, so people with real problems that are actually taking leadership in this realm. And we want to bring you 2 of the top startups in this field that are colleagues. We work with them, and we think are going to be big in this field. So that's the day for us. And the first in line is our colleague from D-Wave, Axel Dian, who is Staff Technical Account Manager for Quantum Computing Systems and Services at D-Wave. And he's going to talk about D-Wave Advantage 2 and the technology roadmap that this computing has. So Axel, very welcome. The floor is yours.
Thank you. You have the...
What is the click? Oh, it's over there.
Is it this? Yes, perfect. Okay, can you hear me? Is my microphone on? Yes. Yeah, perfect. Good morning, everyone. Very happy to be here today. So like Erin said, I'm a staff technical account manager at D-Wave. So what that means is my role is working with our clients across the board, so mostly in Europe, but across all types of industry, on helping them understand what D-Wave's quantum computing technology is capable of, but also on finding good use cases where we can start applying this technology to real-world applications. And today, I want to present a bit more about our latest quantum computing technology and capabilities, but really focus on how this applies to real applications that can be useful today. So what I like to start my presentations with is a little bit on why you should care about quantum computing today and now. I hope that if you're in the room today, it means you have some interest in what it's capable of. And as we were just talking about, quantum computing being a technology of the future and a completely different way of thinking about solving complex mathematical problems. I like to bring up one of the research papers that was released last year on proving what we call quantum supremacy. So quantum supremacy is the pinnacle of performance for a quantum computer, and it's hoping to prove that we can solve something with a quantum computer, but you cannot solve with another classical computer. And so our teams at D-Wave worked on the scientific paper, specifically on simulating magnetic materials. I won't go into too much technical detail on this one. The paper is available online. The very exciting part about this is that we compared the Frontier supercomputer at the Oak Ridge National Lab, which is the largest classical supercomputer in the world today, against our latest quantum computer, the D-Wave Advantage 2, on the same type of magnetic material simulation problem. And the results speak for themselves. So extrapolating the runtime it would take the supercomputer to run this same mathematical problem, it would roughly take 1 million years of runtime on the computer and use about the world's energy consumption in energy to solve that problem with a supercomputer. Now, our D-Wave Advantage 2 system, our latest quantum computer, could solve the same mathematical problem with the same level of quality in 20 minutes, and it used just about 12.5 kilowatts of power. So this is what we're aiming for with quantum computing, this revolutionary new way of solving complex mathematical problems in a much faster and energy efficient way. Now, this is the cutting edge of the technology. This applies to very specific mathematical problems that are a very good fit to the technology today. We don't yet see these types of results on all types of application. But when it comes to general application of quantum computing, we look for success in mostly 4 different areas. The first one is being able to solve complex mathematical problems faster. So this is what we call a faster time to answer. So in our supremacy example, we went from 1 million years to 20 minutes. This is in the kind of cutting edge examples, but we do see with our customers today that we can reduce runtime in the tens of 20% faster, meaning that we can run the same problem maybe twice as fast, 50% as fast. Another one is around answer quality. So when you're running optimization problems specifically, it's all about how close you can get to the optimum. And usually it's a trade-off when you run classically between the runtime and the answer quality. So it's both a faster runtime and closer to the optimum solution for this specific mathematical problem. The third one is around lower cost to answer. And the reason to this lower cost to answer is both due to the lower energy consumption. So because quantum computing is very energy efficient, you can solve the same complexity of mathematical problem just a lot more energy efficient with a lot less energy consumption. And finally, it's just around greater agility and flexibility. We're starting to see, even at the commercial real-world use case level, the capability of solving problems that we could never solve prior with existing classical methods. And this really unlocks a whole new type of application and a whole new type of value that you can get out of quantum computing. So hopefully this sums up why you should care about quantum computing and why you should care about quantum computing now. Now, a little bit about D-Wave as a quantum computing company and the technology that we have and that is available to our customers today. So quantum computing is mostly split into two different types of technologies. We have quantum annealing, which is very well suited for optimization problem, and which is D-Wave's original technology. We've been working in quantum annealing since the foundation of the company in 1999, and we believe that this type of technology is production ready today. So today we have customers that access our quantum annealer and that use it for real-world application, that solve real-world problems and get value across these types of problems and perform better than classical systems. The other type of technology is quantum gate models. So these gate models are a different type of quantum technology which can solve different types of problems. So they can do good at differential equations, for example. However, they're about 5 to 7 years away from being production ready in our view. So they're still very interesting for research, but we're yet to get real value out of that. However, as of recently, specifically earlier this year, D-Wave also acquired a gate model company. So D-Wave is now the only quantum computing company that has both annealing technology, good for optimization, ready for industry today, and gate model technology, which is good for other types of application and ready in the near future, 5 to 7 years away. So I'll just very briefly touch on this new technology that's now available as part of D-Wave's technology stack. So we acquired a company called Quantum Circuit Inc. in January. And QCI is one of the world's leading developer for this gate model technology. And they have this technology that we call dual-rail qubits, which allows for error detection within the QPU. And they've had over 3 decades of supercomputing gate model take breakthrough, and they're a spin out of Yale University. And what this means is that now D-Wave is one of the market leaders in supercomputing technology, both for annealing and gate models. So this new technology that we've acquired is, so again, specifically gate model systems, and this dual-rail system, which we're hoping to make generally available this year. And this technology allows you to both have a universal gate, which is a very high gate speed, so up to 1,000 times faster than neural atom or ion technology, but has a built-in error detection, which will be a great leap in performance when it comes to error correction down the line and making this technology available more widely for commercial application. So we are an industry-leading platform for research-focused organizations and HPC centers that are exploring error correction within the QPU. Sorry. So this acquisition of QCI and this gate model technology happened earlier this year. And we have kind of a 3-year gate roadmap at the moment that is made public. So we're hoping that this year we'll get the general availability of our 17-qubit dual-rail system with error detections and error correction demonstrations. There'll be a dual-rail solver that's available on our Leap cloud platform, which is the way you access D-Wave. We'll get a little bit more into that in a minute. And we'll release a software toolkit so that you can build these quantum algorithms on gate models. We're hoping that by next year we get availability of our 49-qubit dual-rail system, and then initial build of our 181, and that by 2028 we get a general availability of a 181-qubit dual-rail system with error correction demonstration on multiple logical qubits, high-fidelity gate operations, and a design with a design ready for over 1,000 qubit DRL processor. So this is our roadmap on the gate model, this new technology that we've started making available to our customers at D-Wave. Now, our original technology, and the one I'll focus more on today, and for which we have many applications and many customers in production today, is our quantum annealing technology. And for this, we're on our latest generation of quantum computer, which is the Advantage 2 system. So it's the new generation of the Advantage system that was released a couple years ago. This one was made available for production applications last year. What's interesting about this Advantage 2 system is that we have about the same number of qubits as we've had before, so around 5,000, but we have higher connectivity and higher coherence on the quantum chip. What that actually means is that we're able to have longer coherence time, meaning that with double the coherence time, we can get faster time to solutions, so we can be even faster to finding optimal solutions to optimization problems. And with the increase in the error mitigation technique and the increase in the energy scale, we get to higher quality solutions. So this is the latest and greatest quantum annealing technology that is available today. And it's thanks to this new development of the Advantage system that we've been able to run and demonstrate this quantum supremacy paper that I mentioned at the start of the talk. So it is really a new leap in the direction of quantum supremacy and quantum utility. Our roadmap for this side of the technology, so the quantum annealing side of the technology, is to get to the Advantage 3 system at 100,000 annealing qubits. And so we have a public roadmap for the next 2 years as well. So this year we're getting an initial design of the samplescape for the technology scaling. So how are we going to design this new chip and scale up from the 5,000 qubits we are at today to 100,000 qubits? We're hoping that across the course of this year and next year, we start having the packaging demonstration of the multiple integrated circuits with a superconducting interconnect. So what we mean by this is we're now interconnecting multiple chips together to be able to scale up to this size. And we're hoping by 2027, we have a small-scale dual annealing processor prototype, meaning that we've proven the capability of connecting multiple chips together and scale up to a certain size of qubits. And like I said, the end target here is to get to 100,000 annealing qubits, which will open the door to many more applications. And what that looks on a roadmap all the way to 2030, with both our quantum annealing systems and our quantum gate systems, is that we've obviously had the Advantage system in 2023, the Advantage 2 system was out in 2025. We're hoping for a performance upgrade by 2027 and the first Advantage 3 processor in 2028 to 2029. We're also hoping for the 17-qubit DRL gate model system out in 2027, a 49-qubit by 2028, and 181 qubit by the start of 2029. And what that also means is that we're also progressing our software stack, which is the Leap platform. So we had our Stride solver that was launched in 2024, which is the new hybrid solver, which I'll cover briefly in a minute. We're hoping to get our Acumen software, which is for the gate model, on board by 2025, and then integrate gate and annealing in the Leap platform by the end of 2026, and then having some new features around machine learning and HPC integrations within the Leap cloud platform by 2028. So just briefly on the technology stack that we have available today for quantum annealing, which is very well tailored optimization problem and can be used for production level applications. So our quantum computer is the sixth generation of annealing quantum computer, currently at 4,400 qubits. This is the core of the technology, and it connects into our cloud service, the Leap cloud platform, which all of our customers use to access the computer, run problems, get responses back. It has a 99.9% uptime, so it's production ready, meaning that you can rely on this technology to actually run large, complex optimization problems, even at a corporate level. We also have developer tools, which is the Ocean SDK, That SDK is available on GitHub, and it is open source, meaning that if you want to have a look at kind of the different tools you can use to build quantum applications, this is something you have access to online. And finally, we offer professional services. We actually have Mayowa in the room from professional services who will be giving a presentation later today. They're a great team that can work with your teams on developing and building applications specifically for our technology. And on the quantum annealing side of the technology, we've got multiple systems that are spread around the world. So our head office for the research and development side of things are in Burnaby in Canada, where we have a few systems. We also have a system in Marina del Rey in California. We now have a system in Huntsville, Alabama. And all of these systems are connected to the cloud platform, and you can access these different systems when you get access to our online quantum computing platform. We do also have what we call on-premise systems, particularly for research institutions, including one at the ULIC Research Center and one in Boca Raton that is being installed in the coming years. Oh, it looks like the pictures didn't load on that slide, but the most important part is the text. So, like I said, and it was shown in the roadmap, our latest generation of solver on our quantum annealing technology is our Stride hybrid solver. So quantum annealing is a very good technology to solve optimization problems. Using the pure quantum QPU is possible, and all of our clients have access to the pure QPU. However, it does require understanding of quantum effects that are in the chip. And it does require a good understanding of the different parameters you can adjust as part of this optimization through the QPU. What we offer at D-Wave is a new type of solver, which is what we call a hybrid solver. Now, what a hybrid solver is a combination of quantum solving technology and classical technology to build an overall optimization tool that can be used by many types of customers. So these are people that have quantum knowledge, people that have operational research knowledge, people that have optimization knowledge, people that have a specific optimization problem that they want to solve using different types of technology. And our latest Stride solver is the most powerful solver we've ever released, and it takes its performance from 4 different pillars of technology. So the first one is quantum optimization. So we are a quantum computing company. As part of this hybrid solver, we offer quantum optimization resources, which allow you to solve these problems much faster, much better than other classical solvers you might be using for optimization purposes. The other part of this is that we also offer specific types of variables. So if you're familiar with quantum annealing, at its core of it only supports binary variable. However, we do know that binary variables are not the best way to represent some optimization problems. So for this reason, we've offered support for list variables, sets variables, but also integer variables. And these are very interesting ways of expressing a mathematical problem in an efficient manner to solve an optimization problem. Like I said, it's a mixed quantum and classical solver. And so for this reason, we offer mixed integer linear programming as part of that solver. So this is mostly a classical method. The idea here is that when you submit a complex optimization problem, there'll be parts that make use of a quantum optimization and allow for a faster solve. There'll be parts that are more linear, which can be solved very well classically, which will make use of our classical algorithms. And then finally, something that's quite interesting, and I already had the chance to talk to a few people about this earlier today, is this use of tensor programming. So there are many applications that can be very well expressed as an operation of multiple dimensional arrays. And for this reason, you can represent your mathematical problems as a tensor programming network. And it's something that's quite common in machine learning, but it's very new for optimization. We've seen some great performance on our commercial applications. So I think I'm closing up on some time, so I'll skip a couple of these technical slides, and I'm very happy to talk a little bit more about that after my talk. What I do want to focus on is a couple of our commercial use cases. So like I said, as of today, we do have commercial customers that are using our technology to solve real-world problems and solve optimization problems using this tried hybrid solver. I've got a couple examples here of 3 of our customers. So we have Patent Food Group, who is a retail company. They're based in Canada, and they've been using our quantum technology to optimize the way they run home deliveries for groceries. So when you order groceries to be delivered to your home, they use the quantum computer to optimize which delivery driver should deliver using which delivery truck from which specific store in what order to what delivery location. And thanks to using our hybrid technology, they've been able to solve this optimization problem 80% faster than they used to do it classically. So these are real-world problems at full scale. Another use case we have is with NTT Docomo, which is around increasing network performance. So this is in the telco business. NTT Docomo is the biggest telco company in Japan, and they are using our technology to optimize the way that they break down the telco grid to be as efficient when connecting to mobile devices. They're a company in production today as well, so they are using this for real customer applications, and they're seeing with our quantum computer about a 15% increase in network performance. The final use case we have here is a use case we've done with Ford Otosan, which is a manufacturer of Ford vehicles in Europe, based in Turkey. And for this one, it's a manufacturing use case. So they're using our technology to optimize the way and the order in which they manufacture the different vehicles on the factory floor in a way as to be as efficient as possible. And something that they've been able to do is to schedule all 1,000 vehicles that will be manufactured that day in less than 5 minutes using our quantum computer, and meaning that we can actually rerun this multiple times across the course of a day. So they can re-optimize their factory floor as new information comes in. And so these are examples of where you can apply quantum computing and quantum annealing with this hybrid solving technology to different real-world applications. The last thing what I'll leave you on is what makes good use cases like this. So you'll see on this slide the use cases we've just talked about: NTT Docomo, Ford Otosan, Patent Food Group are all on here. Where we see really good success with optimization using quantum annealing is in these 3 types of problems. So we have optimization problems in general, where you're trying to maximize or minimize an objective. We have permutation problems, such as flow shop scheduling, which is what Ford Otosan are doing, or workforce scheduling, which is the Patent Food Group example. And we have combination problems, such as the network partitioning at NTT Docomo, or even community detection in power grid applications. So hopefully this gives you inspiration on where you could apply quantum annealing and quantum optimization within your areas of industry or your areas of research. And I'll leave it to this. Thank you.
Thank you, Axel. Now, this was interesting, wasn't it? Okay, this was interesting, wasn't it? Yeah. I hope you hope you understood half of it or some of it, but it's about giving you some inspiration and some ideas. Even if we don't understand everything that Axel was putting in front of us, there is definitely a roadmap. There is some achievements, and we're going to see in the second half of the day more about practical applications and use cases with this technology from people that is in the audience. Now, what's in a name? What's in a name? For those of you that don't know, Muriel Latane is our next speaker. She has been working in the European battlefield for many, many years, representing the voices of the research and technology organizations like TECNALIA. She's been championing our role as key organizations or key elements in the knowledge transfer process, and how technology gets it makes its way to industry. She is the Secretary General of EARTO, which is the European Association for Research and Technology Organizations, and then she's a very nice lady. So we are very lucky to have her here today. She's going to give us a talk about the role that RTOs play in this ecosystem, designing the technologies and designing the strategies. And yeah, the floor is yours. Thank you.
Thank you, René. I hope you can hear me fine. Yes? It's on? Okay. We don't hear it, that's why we check. And they didn't kidnap the two other speakers, they just have to make a video. So Jesus and Axel are coming back, because you see them going after. So I will have to do the same, but I come back, so if you have questions, please feel free. EARTO, so who are we? It's the TECNALIAs of Europe which are putting themselves together, and it's the whole of TECNALIA and a whole lot of more applied research centers together. We are about 350 in Europe. We are representing about 32 countries. And some of them, not all of them, they also do stuff on quantum. So I'm here to explain you a little bit what they do in the ecosystem and so how they can help you. You could translate that with the support of TECNALIA and the other members of BRTS and what they do with quantums for you. So what you see is that applied research centers like TECNALIA, we have different jobs, and the job is to help scale up tech, but we're not doing the product and the services. You, industry, do that, but we are doing the maturation of tech with you and for you. So we're working with, for example, TECNALIA works with D-Wave, use the D-Wave technology, and help you to see how could you use D-Wave more and have different applications set up for your sector. This is the precise role that RTOs are doing, and we do that for so many techs. Quantum will be one, but as you know, TECNALIA is also working on many other techs. So whatever tech is being produced in Europe, we have probably one RTO behind somewhere. If not one, probably multiple in different tech, and they are exchanging also their own knowledge and trying sometime in combination of few RTOs together to help different clients. So that's what we do, and to do that, we have labs and we have people. When I have to describe, I say, you know, we have a lot of infrastructures. They are very costly. In general, we have them because they are too expensive for one industry or one company to pay them. So we take the charge. It's what we call a market failure. That's what we exist, is because company cannot afford that. So we mobilize resources in a kind of one-stop shop where different type of industry, the large ones, but also the SMEs can come in, and we are manager of those labs. It does not always happen in academias. In the US, you have different system where university takes the job of the university in Europe and the RTO, but in Europe, we have two different systems, academia and RTOs next to it. Why? Because some of our labs have to be open 24 hours in the day and 7 days a week. This is not what you do in the academic fora. So that's also why we have been created. A lot of the RTOs have been spin-off of very famous universities. If you take in Semicon, you know IMEC, that was 30 years ago a spin-off of the KU-Leuven. Why? Because the clean room is quite complicated to manage, and that's why you need different type of people to do that, highly technicians, and the skills of researchers. So that's what you will find in RTOs. I think that's what you find in the different environments and what you find in quantum today. So how do we work? To do that job, we have a special funding mix. We get money from the region or the country, depends the size of the RTO and where we are located. And to do that, we try to scale up. We do with national or regional programs, you know that very well in the Basque regions, and we do contract with industry. So we are also financial engineers around certain technology and also certain labs. It's complex, it's not an easy way of working, but that's what we know how to do, and we are quite specialized in that financial engineering to match your take over the whole valley of death. It's explained a little bit how we work also with companies. What we also do, and you see that in terms of for the quantums, we are not only doing cross-fertilization of technologies, but we do also cross-fertilization in applications. So you are today looking at quantum, but you're coming from very different companies with very different use cases. So it's one technology, many field of applications, but also to work on quantum, you had many different type of expertise needed. So what you see is this is the type of, I call it, you know, Shiva type of things where we have many arms. That's what an RTO is around, you know. Industrialization. Yeah, but deep tech research. But then also basic research, because quantum still is used a lot of basic knowledge that still need to be developed for the future industrialization. And we need to understand as much as the industrial problem, as much as the very scientific basic system that goes into the quantum computer. This is what you find in your TECNALIA environment. So that's what RTOs are offering. It's not an easy fate to do. We had a lot of discussion on the management of the RTOs. How do you find all this type of knowledge and where do you put the emphasis? You can imagine that it has a lot of discussion internally. What we also see is that what you're seeing now, you have an event on D-Wave, which is coming from Canada, if I'm correct, also in the US, based in the UK, coming to talk to you here in the ecosystem, in the Basque regions. And I'm discussing Europe because TECNALIA on Quantum is working in my task force with 35 other RTOs to discuss the future of the quantum strategy in Europe. That will probably discuss which type of base system to use, such as D-Wave. This is very typical of what RTOs are doing. And I think today is a good example of trying to consolidate different level of where the knowledge may be, where the technology you need to have as company are, and to bring them back to the regions or the country where they originate. That's also the job of RTOs, and to help industrialization within their national and regional ecosystem. So I think it's a very typical example of what RTOs are doing is actually today. What do we do? As a network of all these applied research centers, we have the job, we are a trade association, or let's say the syndicate of applied research institute in Europe. And what do? Is that we pool our members to tell what are the key elements on which we have to work. Sometimes it's about how do we function, but sometimes it's about what Europe's strategy on key technology should be. So we had something on quantum. And what we did is that we work with working groups or task forces. How do you want to do it? It's a kind of coordination of the expertise that exists within our network. When technology are so new, you can imagine that we have a lot of different babies, like you would have the national or the regional industry clubs that some of you may be. You also have the national industry club, and you have the European industry club. Well, you will have the BRTA to help you here. You have TECNALIA, BRTA. You will have FEDIT, for those who knows, which is the National Association of RTOs in Spain. And I'm the European. And sometime our sector has to orchestrate itself on technology at European level, and we are not yet there. That's the job of EARTO. So quantum was quite new. Commission was thinking, I need a new strategy on quantum. That was out in July. So they came to me in January, say, Muriel, I need you to give me a roadmap. And I'm like, okay. So I turned to my members, who's doing quantum? So we had a task force on quantum. We had about 50 experts, included, of course, the colleagues of TECNALIA, but you see we have many other RTOs working on quantum, and we provided our view on what, the next strategy should be on the technology on quantum. Now you have a quantum strategy, you have a quantum act also coming up, where they are discussing what to do. They have financed 6 pilot lines. TECNALIA is involved, I think, in at least 2, Jesus, you tell me if I'm not wrong. So we have, all our members are in the 6 quantum pilot lines, TECNALIA being in 2. They know exactly what happens also in the other quantum pilot lines, discussing what are the other testing and technology being piloted. They are discussing industrial roadmap of those technologies. So this is where you see that sometimes you need the European environment to be able to look at what will be, maybe the best technologies for future industrialization. And that's where the role of TECNALIA is to look at what those are, and also to provide you back the feedback, you as industry who wants to scale up, maybe what are all your options on the market at the moment and how to best use that. So today you have the presentation of D-Wave, and I'm sure you have more areas to look at. So that's what also my network is trying to do, to pull people. My job is also to show what we can do with the technologies we are developing in general, what impact. So we have a lot of activities. You can see that on our website. But what we are trying to show is how can you work with institutions like TECNALIA? And we have different models. We did quite a lot of success stories, and I want to pin one that is on our website. Please have a look. Basically, there is 3 ways to work with RTOs for industry. Or you go, it's a large company, often it's more large than small, direct with one company or medium-sized one who knows exactly the problems they want to solve. They have the idea for a new product or services. You have a very easy direct contract, and sometimes you scale up a whole new area in the RTOs. I give you an example. Years back, I used to work in automotive. There was no EV. Renault and Peugeot in France were not doing EV, and they say, oh shit, we're going to miss the wave. They kind of missed it compared to the Chinese, just didn't go as fast as them. But they asked the CEA to develop a complete new lab that did not exist, to try to work from the materials in the batteries, to create the batteries, to test the battery in the car. And the CEA in 6 months had a new pilot line for the French industry to test the batteries for EV. So this is a demand from the industry. It is not yet there. The RTO is discussing with the national or regional government on how to scale up, and you have a new labs where then the different industry comes and where all the SMEs and the suppliers of the automotive chain, for example, came to work. So you have one type like this. This is the first one. I should maybe go to this. Oh, I see. Like the previous speakers, there's a lot of things that don't show. So let's stay to the first one. No, I have to go the other side. Okay. It doesn't want to. Doesn't matter. If you go back to the slides where I wish was. So the second business model, or let's say way of RTOs to work, is not to go from the scratch to discuss what you have a whole new pilot line, for example, or research infrastructure or technology infrastructure. The other way is we mature the tech. For quantum, you guys are starting to look, but TECNALIA has worked many years already on quantum before you go to the industrialization. So the role of the RTO is to mature the tech also in-house, do part of the value of that before the industry may be interested. So when it comes to, let's say, TRL level where it is more discussable with industry, then come the discussion. Maybe I go to the right slide. Let's see if that works. I will not go too fast. Yeah, so that is the second bullet, where then we nurture the technology, and out of that then come the discussion a few years later where we say to industry, maybe wake up, now we will start to be able to think of nurturing a little bit of tech and implement. We do that. Sometimes we do that with large company, a lot of the SMEs, and sometimes we think, okay, we have to look with startups because the industry is maybe not ready, or we are going to do a new modelization tool that maybe needs to be industrialized with companies. So we do our own startups, try to find some VC money investments. We do that also with our own scale-ups. And sometimes what will happen is you have 2 research centers that by combining their resources, and I know you have an example of TECNALIA, I think with RECAT or with LEITAT. With RECAT, I believe you have one spin-off together where you combine 2 types of knowledge and technologies, and then we come up with a new spin-offs that then will provide new services to industry. So there is quite a lot of different models on how we can collaborate with you as industry, and this is what we try to show. So if you have to go, maybe this one works now. Yeah, go and have a look to our website. Click on the TECNALIA one. We have the #2 site, for example, which is an example, but you can see also the different ways we help technology to mature and how do we scale that up with you to industry scales, mass productions, products and services that then are used. And I think that's what we do with colleagues, for example, of D-Wave. So to show you a little bit of what we do, and of course, events are always there. We have another conference coming up soon. But what we do is that we do by putting our members together. This is the job of our network. That's what we did with Quantum, to try to push to have investments in Quantum at European level, being sponsored by pilot lines that puts actually a lot of RTOs together. So they can actually offer you the services afterwards of what you're discussing today on the application of Quantum for your own industry. And I think that's the key job of what my members are doing, and today is quite a good example. And at least you know that in quantum, we try to push for more European investments. I think that has been the target for a few times. So thanks. And so I don't disappear. You will.
Thank you very much, Muriel, for giving that overview of the role that RTOs play in Europe, and not to repeat her keywords, ecosystem integrators, and this idea that we've been working on these technologies for years before putting them in front of yourselves. So that's the role we play as an RTO, and that's an important message as well to take forward. Okay, we have last talk before the coffee, proper coffee, right? And some biscuits. I'm sure we'll need a bit of sugar to keep the day going. I'm very pleased to have here Cristina Murillo. She's Managing Director of Cluster Gaia. It's a person that has been working very closely with her colleagues in putting the ecosystem together. She's going to give some examples, and she's going to give us some numbers. And here we have the opportunity to see how important and what a big effort this region has been doing to bring quantum technologies to industry. Cristina, the floor is yours. Thank you so much.
So, good morning, everyone. Thank you very much to TECNALIA to invite Gaia. So, let me to start just to say some words about the Basque Country. Basque Country covers just over 7,200 square kilometers, more or less, and inhabit 2.2 million people. So it's a small territory, but even that, it has a very strong research, technology, and innovation ecosystem. There are some figures. For example, it has 125 entities in the Basque science and technology systems. It has 9 Basque excellent research centers, 4 cooperation research centers, also 4 universities with over more 67,000 students, and 9 public research entities, a lot of data. In the case of Gaia, as a cluster, also the Basque country has 17 clusters. Gaia is one of these clusters, and we say that we represent the knowledge and applied technology industry. As you can see, this is our ecosystem of Gaia. We start in 1983 in the electronic sector because of lack of talent in electronics. Then we have the informatics, ICT, telecommunication, engineering and consulting, and we are working under 4K technology. One is the IoT, the other is artificial intelligence. Also in the Basque country, we have the Basque Artificial Intelligence Center. We usually collaborate with them. Later, I'm talking more about the bike. The other is the artificial intelligence, that means augmented reality, virtual reality, digital twins. And we have another one, is very transversal, is the cybersecurity. In 2020, we create a small cluster, belong to Gaia, is the TBAS. And more or less also 3 years ago, we started working with the quantum technology. Why we started with quantum technology? Well, sorry. First of all, just to tell you about some data about Gaia, the sector. We have more than 3,000 and almost 7.5 million euros in turnover. We represent more than 300 companies, more than SMEs. We have some small companies and others bigger. We have more than 27,000 professionals. 70% are coming from the university, 36% are women. So we have also some programs to involve women in our sector. So this is more or less just the dimension in data about the sector and about Gaia. And I am asking, why is a mandatory or needed to have a Basque quantum strategy? Because first of all, we are convinced that the quantum technology is not only the future, it's also the present. And the quantum technology play a fundamental role due to its capacity to generate economic and social impact. Also, we understand that the Basque country has a very well-defined quantum technology. We have different strategies, Basque ICUR, BeKind, IBM, Allianz, later I'll explain them. And all of them have the opportunity to create a new companies specialized in quantum technology and to create opportunities in the Basque Country. In addition, it can generate quality jobs and also being a region that plays an active role in the global development of quantum technology for sustainability and for the common good. So this is one reason that we understand that the Basque Country is one of the driving forces of industrial and business growth and prosperity. As I mentioned, some example, Basque is one of them. It has the commitment to position the Basque Country as a pole of international reference in the development of quantum technology. Its own mission is to create an ecosystem of research, talent, and innovation in quantum technology with sufficient critical mass and connected internationally so that it can become a pole of attraction for the brightest research from around the world and for the development of business opportunity. But I say that is not the only. Well, in that case, thanks to Basque, we have in San Sebastian a supercomputer. It is the IBM Quantum System 2. It's the first supercomputer in Europe because of its characteristics and functions, and is the third in the world. The other two are in United States and in Japan. And nowadays, this supercomputer is using not only for research, also for the industrial. People who are working in industrial are using this computing also. But I mentioned that is not the only strategy. We have another more. For example, we have BeKind. It's a Vizcaya quantum strategy. It's really a strong one. It's helping or put funding to promote proposal projects, give the opportunity to the company to have access another platform of quantum platforms, not only IBM, but also others. It promotes the use case, support also to the startup. We have also the Gipuzkoa Quantum Hub. Again, it's helping a startup. They promote to create new startups in quantum technology. They put some funding. The other initiative is the Basque Artificial Intelligence Center. In that case, as I mentioned, as Gaia, we collaborate with the BIC. And also it's quite important because if we want to have a quantum technology, we also need the artificial intelligence. So I would mention it because we understand that it's very relevant for our ecosystem. The other is the Basque Cybersecurity Center. It has different, for example, protection of infrastructures, protection of public and business data, prosecution of cybercrime, for example. And we have others. We have the photonics community. It was composed by TECNALIA, for example, the Basque Public University, Donosti International Physical Center, and others. The other, we have, for example, the different quantum sensor laboratories. TECNALIA has one. We have another research centers such as Techniker, CEID, the Basque Public University also. And then we have the group of Gaia, I mentioned at the beginning, and we are the ecosystem for the integration of quantum technology. So, also in the Basque Country, we have different infrastructures. We have, I mentioned, the quantum computers. It was in San Sebastian from last year. It's an agreement, an alliance between Iker Basque. Iker Basque is a science foundation, was created by the education department of the Basque Country and IBM. We have another laboratories. They are new for sensor, computing, communication, quantum literacy. They are Maria Goiri. Is in the campus of the Basque University, Basque Public University. And we have another, for example, the Quantum Research and Innovation Lab is in TECNALIA. Then not only this infrastructure, we also have another platform, tools and frameworks. We have some, for example, D-Wave, Honeywell, Pascal, and thanks also to the BeKind that has an alliance, an agreement with all these organizations and allows the company to use these platform, tools, and frameworks. And we have another, such as Telefónica, Fujitsu. So we have a strong ecosystem in quantum technology. Then our areas of specialization are more or less quantum simulation, quantum computing, sensor and metrology, quantum communication, and post-quantum cryptography. All of them are applying in different industries. In energy, we have some example, in automotive, in life science, in information technology, aerospace. So then I bring a project that we are working on it, and we have some example of this. Then this is a picture just to show the ecosystem of the quantum technology. We have more than 17 users, companies that are use this type of technology. We have also another providers, but for example, I pass this. This is the ecosystem of quantum startups. I know that there are more, but it's a good representative of the quantum startups in the Basque Country. I think later in the afternoon we have the opportunity to have some of them. As I told you, now I'm going to talk about the APPTC project. It's an alliance, it's a public-private alliance in quantum technology. This project, Gaia is leading it. Last year, at the end of last year, this project we present a call for the Red Point S. It's a business public entity attached to the Digital Transformation and Public Administration Ministry. And in this project, we should develop 36 use cases. 70 are developing in the Basque Country. The others, for example, 2 are developing in Andalusia, other 2 in Asturias, 4 in Castilla-La Mancha, and 1 in La Rioja. But for all these 36 use cases, 70 are developing in the Basque Country. So again, we think that we have a strong ecosystem to develop this kind of project and initiatives. Then I put some example of the use case, but also around in this project, around the project, not only we are developing this use case, we also are developing some training programs, because we understand that we need to acquire some knowledge around quantum technology. So now we are working just to developing these training programs. And also we are developing a study just to know and to understand the quantum technology in a national level. The use cases are developing in different specific sectors. One is in manufacturing, and for example, these use cases are working on assembly, maintenance, quality inspection, resource allocation, industrial logistics. The other is in energy, just to power grids, renewables, ports, hydrolysis, and operational efficiency. The other is in logistics and transport, also linked with the smart mobility, just to apply in separate chain, last mile delivery, routing, urban traffic, heterogeneous fleets. So you can see that there are a lot of use cases working in this project. Other areas, finance, customer analytics, fraud, risk assessment, pricing, financial recommendation is another way that quantum technology is using in financial sector. The other is in telecommunication and IT, network, data center, cookie, the satellite imaging processing, the other is in e-health, biotechnology, pharmaceuticals, defense and security, aerospatial, and there are others linked with water, environment, construction, science, so retail and agri-food. So there are a lot of sectors that nowadays are applying this technology. And just, well, here we have some news. The first one is the alliance between Airbus and the strategy of Basque with IBM. The other is some news about this project, that APPTC project. So well, you can see different news about quantum technology that with telling us some things that are happening in the region. And just to finalize, we understand that it's very important to have infrastructures, to have access to different platforms, tools, frameworks, but it's not enough. For us, it's mandatory. It was the reason that I mentioned our picture as a cluster, that at least three technologies, that is quantum, but also artificial intelligence and microelectronics, should work together. Because, as I mentioned, we need to create or to have a quantum technology. We need, first of all, to have the artificial intelligence. That means, for example, artificial intelligence embedded. And also we need to have semiconductor chips. So all these three technologies or industry should go together. This aspect, we had the opportunity to defend in a multi-level governance in Bilbao this year. It's called the Bilbao Declaration 2026. And another regions from Europe defends this, it's not an idea, maybe it's this concept, no? And all this region has the commitment to develop different action working on that line. The first one is recognizing and strengthening regions as European hubs for technological integration. The other is promoting the stable public and private coordination mechanism. The other is developing integrated European roadmaps for the quantum, AI, and microelectronics triad. So this is very relevant. The other is the strengthening the industrial dimension of quantum technology beyond computing. Then creating and supporting European academies in quantum technology and also in artificial intelligence. The other is the promoting the flagship project and industrial pilots at European scale. And the other is developing the use case in quantum technology or advanced artificial intelligence. So in that way, we understand that can be the one road to develop the quantum technology inside the region, inside the companies, inside the cities, inside the whatever. So this is all for my part. So thank you so much. Should I go?
Sí. Thank you. Thank you very much, Cristina. Just in time, I mean, we got a couple of minutes before coffee. I'm going to take the advantage of saying a few things. Actually, I've realized that I haven't introduced myself. I'm introducing everybody and you don't know who I am. My name is Irene López de Vallejo and I'm the person that leads the quantum technologies efforts of TECNALIA, which means those efforts outside with clients and institutions in the world, but also the efforts inside, in-house, to work with different markets, to reach out to you people, the people in this room, because many of you have been invited by our colleagues inside TECNALIA to come here because they thought this was an interesting opportunity for you all. So that's me, Irene, remember me. I'm going to be here with you all day. And now we have coffee, but before that, I want to make a comment on Cristina's presentation, because the regional ecosystem that she presented is like really, really strong, and not all of the actors that have been presented on those slides have been given its rightful, let's say, limelight, because some of the actors have put more effort than others in bringing this ecosystem together. And particularly here in Vizcaya, we have a very, very strong ecosystem. People really, really looking after the community and investing on those use cases that we're going to show later today. And we have some of the representatives in the room. I also want to say that some of my colleagues in the Quantum team are here. Could you please say hello, hands up? Yeah. Okay, thank you. Yeah, so you can reach out to them and say hello, and then some more to come to the coffee and the biscuits. Yeah, I'm going to be your host for the day, so I'm sure I'll have more interesting stuff to tell you later. But please reach out to the speakers here in the morning, people from the Wave, because that's a great opportunity to talk to them, but also to the people that are going to speak later. Make questions and get interested about what their work is and why are they working on this area and what have they learned. This is a unique opportunity to talk to each other. So please, coffee biscuits. At the end, you have a very nice terrace with views over the Basque Mountains. And yeah, be back in half an hour. Thank you very much. Okay, thank you very much. Welcome back, everybody, here and at home. After this break, we have the second part of the day, from science to industry. So expect some very technical talks that are going to give us some insights on this technology and how it gets applied to industry, because today is about applying this type of technologies to industry. I want to introduce you to someone that is one of the top minds working in this field. Actually, the next three speakers are doing top-notch research in this space. Sebastian Schulz is a quantum algorithm scientist at Jülich Supercomputing Center. I'm not going to say it in German, I can't. And he's going to present us his work and how this is propelling quantum annealing. Please, welcome, Sebastian. It's gone. Where is it? Oh, it's there. Okay. Just a couple of seconds. Thank you. The floor is yours.
Irina just said this will be a more technical presentation, but bear with me, I will try to make it easy to follow, I hope. So, I will talk about quantum annealing and quantum optimization. In recent years, we have seen great improvement when it comes to quantum annealing hardware. With the newest generation of Advantage 2 system from D-Wave, we just heard this morning, we have now access to over 4,400 qubit, 20-way connectivity. And what this means is that we can now try to embed and target large-scale optimization problems with numerous constraints on today's quantum hardware. So let's take a look at some examples. So I prepared here three types of optimization problems. On the left-hand side, you can see a spin glass instance where we use the full Advantage chip over 5,000 qubits. In the center, we have a factorization instance, so integer factorization using around 1,200 qubits. And on the right, we have a rather small 24-qubit aircraft scheduling instance. You can see the embeddings. I have a pointer as well. Maybe not. So in the top plots, you can see the embedding, but what I really want to focus on today are the plots at the bottom. These plots tell us how well the quantum annealer actually performs when it comes to solving these problem instances. Each dot, so the blue dots, and on the right plot here, the red dots, is a single sample from the quantum annealer, so a single computational basis state. In total, we performed here 10,000 samples from the quantum annealer. On the x-axis, you can see the Hamming distance to the solution state, which is this black dot over there. Hamming distance means the number of qubits that are in a configuration that does not match the solution state. So the larger this number, the worse the result. The further away we are actually from solving the problem. On the y-axis, we have the energy distance to the solution state. And when we look at these plots, there are two observations that we can make. The first one is that the quantum annealer is able to produce low energy distributions. So when we take, for example, the spin glass problem, the total energy range goes from 0 to above 20,000. And you can see here, on average, we sample states, let's say they have an energy distance on average of like 60, 70 maybe. So this is already very good, especially when we consider that for a single state, it takes us around 2 milliseconds compared to roughly a minute when we would do this classically, as I will show later. So this is already very good. The second observation that we can make, however, is that for none of these problems, it doesn't matter if it's like the small aircraft scheduling or the very big spin glass, the quantum annealer does not find the solution state. So we can prepare this low energy distribution, but we actually don't sample the grounds at the solution to the optimization problem. And this is a very common observation that we make, that we can get this low energy distributions, but really solving the problem is quite difficult on the quantum annealer. And this is exactly what I want to talk about today. So I will show you how we can enable the quantum annealer to go from this semi-optimal distribution to a distribution that actually allows us to obtain the solution state. So let me introduce you to learn-driven annealing. This is an iterative quantum annealing algorithm that we developed in Jülich. The idea here is that instead of just focusing on the best state that the quantum annealer produced in the sample set, we consider the entire sample set, so all the 10,000 samples that we get from the quantum annealer. We do this because these samples tell us a lot about the optimization problem. They tell us about the energy landscape, maybe the position of minima and so on. And based on this information, we can then modify the optimization problem and make it easier for the quantum annealer in the next iteration to find lower energy states and eventually solve the problem. You can see learn-driven annealing in action in these animations here. So again, we start with this semi-optimal distribution, so the blue dots, and over the course of several iterations, you can see that this distribution approaches the solution state until the solution is found with a very high probability. Learn-driven annealing does this by focusing on the main bottleneck in quantum annealing, and this is quantum phase transitions. Quantum phase transitions play a very important role in quantum annealing because they essentially describe how the search space is explored in the algorithm. So you can see here a small example. We'll look here at the 20-qubit spin glass instance. On the left-hand side, you can see the energy landscape. So this x and y-axis, think of it as the state space, the Hamming distance. So all the state configurations live in this plane. On the z-axis, we have the energy. So this energy landscape is basically what a classical solver would also see when it tries to solve this problem. You can see that we have several minima in here. Maybe you can use the pointer here if it works. So this one here is the global minimum, and then we have a local minima here and a local minimum down here. So this is the classical picture. Here on the right-hand side in this top plot, you can see the instantaneous energy spectrum, and this is more likely what a quantum annealer actually sees when it tries to solve the problem. You can see that we have here three curves highlighted in blue, red, and green. I did this because these energy levels actually correspond to the minima. So the blue line here is the state that ends up in the global minimum. The red and the green one are the ones that end up in the local minima. In quantum annealing, what we do is we have an adiabatic time evolution. So the system starts in the instantaneous ground state at the beginning, so all the way down here. And then it evolves adiabatically, so following this red curve here. You can see that at this position over here, we get, or we find our first closing energy gap. This is what we call an avoided level crossing. This is quite large, so it's easy for the quantum annealer to evolve adiabatically here and just stay in the red state. However, we have a second crossing that is with the blue curve. Maybe it does not work. So it's with the blue curve over there. This is a very narrow crossing, and what happens here is that the system transitions from the red curve into the blue one, and then evolves until the end of the evolution. And these two closing energy gaps, this is what makes quantum annealing hard, and they are related to quantum phase transitions. So this first one is what we call a many-body localization transition. This is a second-order quantum phase transition, and what's happening here is that initially the system is in an equal superposition kind of all the energy wells in the system. You can see this on the left-hand side in this plot. We have initially probability mass that's across all the energy wells, and over the course of this avoided level crossing, you can see that all this probability mass ends up or localizes into one of these wells. And this is exactly this local minimum that corresponds to the red line. In this case, because the wells have different shapes, that's the main characteristic here, all this probability mass ends up in a local minimum. So when the quantum annealer tries to solve this problem, it actually localizes in the wrong state. And to fix this, there's the second transition that happens in the annealing. This is what we call a tunneling transition. So here the system goes from a localized state on the top and tunnels through this large energy barrier into the global minimum. And this is a first-order quantum phase transition. It's very hard to do on quantum annealing. So typically what we see when we try to solve such a problem is that the quantum annealer does the localization in the local minimum and then just stays in there because it cannot really do the tunneling effectively within the coherence times that we have available. So in order to fix this, what we need to do is we need to increase the gap sizes here, especially for the tunneling. And typical approaches here is to add another term to the Hamiltonian, so some new dynamics to the system. But this is very limited when it comes to the real device. We cannot just play around and add some new dynamics to the system. So instead, what we are doing is we focus on the optimization problem itself. Because what we just saw is that these avoided level crossings, these quantum phase transitions, are related to the position of and the shape of wells in the landscape. So by changing the energy landscape, we can actually modify how the instantaneous spectrum looks like and make it easier for the quantum annealer to solve these kinds of problems. And this is exactly what we do. In order to do this, what we do is we focus on what we call features. So here on the left-hand side, you can see the problem graph of this 20-qubit spin glass. Shown are all the biases, all the couplers of this problem in this circle. And the feature is now a subset of these biases and couplers. And when we take a classical computational state, so just a normal bit string, and we go through each bias and coupler, we can decide whether this coupler, this term, is satisfied or not. Satisfied in this case means that they give a negative energy contribution. So let's look at some examples. If we take the local minimum up there, we get this set of features. So this subset of bias and couplers is satisfied. If we take another state, like the global minimum over here, you can see we get this different set. And as I go back and forth, you can see these sets are completely different or disjoint. However, if I use or consider another set that belongs to the same well in this case, you see that I get a set of features that is very, very similar to the one of the minimum it belongs to. And this is a common observation that we can make. So whenever we have an optimization problem and there's a value, so a minimum, local minimum, or global minimum, there's a characteristic set of features that is satisfied for this specific state. And the set of features actually identifies this valley, this minimum in the Hilbert space in the energy landscape. And another observation, or very important point here, is that the features are all the terms that give us a negative energy contribution. So they are actually the ones responsible for creating this well in the landscape in the first place. So if I would go and just remove all these terms, then I wouldn't get the well. So it would just make the well flat in the landscape. And this brings us to the idea of a feature Hamiltonian. So what we do here is we take a classical state, like this red one over there. We go through all the biases and couplers, and we set all of them to 0 if they're not satisfied, so not a feature of this state. And what this does is shown in this animation here. So this is an interpolation going from the original problem to the feature Hamiltonian. You can see as we transition to the feature Hamiltonian, we are deforming the energy landscape. And in fact, we are removing the two minimas, the two local minimas that we saw before, so in the center, top and bottom. Okay, so you can actually prove that the energy landscape by doing this becomes completely monotonic, convex, so it's also classically easy to solve. We saw before that the relationship between valleys, between these minima, is responsible for creating this bottleneck, so this phase transition in quantum annealing. Now that we remove them, let's see what happens to the instantaneous spectrum. And this is shown here. So this top plot shows you the instantaneous spectrum of this modified problem Hamiltonian. You can see that this red and this green curve, they gradually move upwards. And these curves, as I said in the beginning, correspond to the two energy minima to these two wells that we just removed with this feature Hamiltonian. And by doing this, eventually this blue curve, which is the global minimum, becomes the instantaneous ground state throughout the entire anneal. What this means is the system is initially prepared basically in the solution state, in the ground state, and it can easily stay in this ground state adiabatically, even if we have short coherence times, a noisy system. It's easy to solve for the quantum annealer now. Okay, and if you do it perfectly, you even get like really straight lines in the instantaneous spectrum, so it's really easy to solve. Okay, so we modified an optimization problem, and the modified problem is easy to solve. But what does this all mean in terms of the real problem that we wanted to solve initially? And this is shown down here, so on this bottom plot. What's shown here is the instantaneous spectrum of the original problem Hamiltonian. You can see that this blue and red and green curve, they do not change as we transition here to the feature Hamiltonian. The only thing that changes is the yellow curve. This yellow curve is an annealing simulation done on the feature Hamiltonian, so this modified problem Hamiltonian, but re-evaluated in the instantaneous basis of the original problem. What this means is this yellow curve tells us whatever we do here, what does this, what these dynamics would correspond in the original problem. And you can see initially when we're just having the original problem Hamiltonian, we're just following this red curve here. So as I said in the beginning, this many-body localization here, this is something that we can easily do in quantum annealing on the real device. But the tunneling later, this is where it fails, so it just excites into the first excited state. But as we transition here into the feature Hamiltonian, you can see that we force the system out of the red curve into the blue one over here, where it then stays until the end of the anneal. So what this means is, using this feature Hamiltonian, we just modified the dynamics of the quantum annealer in this original problem. So it's independent of what the coherence time is, how long we or how fast we do the annealing. We can just tell the system, if it fails, what to do and how to behave at these bottlenecks in the annealing simulation. This is just one example. We could also use, for example, this local minimum over here. And as we go here into the feature Hamiltonian, you can see that we force the system out of the red into the blue curve and eventually into the green curve, where it then stays and ends up. So you can really think of this feature Hamiltonian as a tool that we can use to manipulate the dynamics or how the system behaves when it does the annealing. Of course, this tool alone does not solve any optimization problem. We just used here a state that we already know. So we use this to design what we call protocols. We have 3 protocols: local search, global search, and tunneling search. And these 3 protocols allow us to explore the instantaneous spectrum in a very systematic way. So we have the local search. This focuses primarily on transitions that happen at the end of the annealing. So these are transitions that keep the system from reaching the minimum, but reaches some excited state within a well. We have the global search, which targets these many-body localization transitions. So this allows us to transition from an energy well into another energy well, even if they are thousands of Hamiltons or thousands of spin flips away. That's something that's classically very hard to do, but with the quantum annealer, since these states are within the instantaneous spectrum, relatively close, we can make these large jumps through large energy barriers. And finally, we have this tunneling protocol, which targets these first-order tunneling transitions to keep the system in the instantaneous ground state. And by using a combination of these 3 protocols, we can basically solve any optimization problem, because we don't focus on specific problem aspects, but rather on the bottlenecks, so these phase transitions that make quantum annealing hard. So let's look at some benchmarking results. What I have here are benchmarking results for the large spin glass instances. We use here not 7 instances, which means that all the biases are set to 0 and the couplers are chosen randomly, antiferromagnetic and ferromagnetic. What this means is that for the spin glasses, we get rather large spin domains. Sizes are around 500, 600 qubits. And this means that we get millions of local minima that are low in energy but have large Hamiltons, so large energy barriers between them. So this makes it both for the quantum annealer but also for classical algorithms quite hard to solve. You can see here in the the top plots show the results for one of these problem instances that we considered. On the left-hand side, you can see the results for learning-driven annealing. Here in the center, you can see other quantum solvers: normal forward annealing, reverse annealing, cyclic annealing is what we tested. And then we also tested classical solvers, simulate annealing, as well as some proprietary solvers from Gurobi, Velox-Q, Toshiba, and D-Wave Hybrid. Starting with learn-driven annealing, since these spin glass problems do not contain any tunneling transition, we use here a simple alternation between our local and global search protocols. And I believe after roughly 50 iterations, we find here the solution state, which took us around 6 minutes to do on the Advantage 5.4 system, so the old Advantage 1 system. When we compare this to the other quantum solver, so here in orange, we have forward annealing, so just normal annealing, just sampling 10,000 states. You can see, as I said in the beginning, we just get this semi-optimal distribution, but there's no chance that we can actually reach the solution state using this method. We then tried reverse annealing. What this means is we take the best state, we anneal backwards, let the system thermally relax to a lower energy state, anneal forward again. This can improve over forward annealing and was the go-to way to do a few years ago. But this is fundamentally limited by the effective temperature of the chip, so we cannot reach here arbitrarily low energy states. We then tried cyclic annealing. It's a relatively new approach that combines reverse annealing with the H-gain feature on the D-Wave machine. So it's basically reverse annealing with some biasing of the qubits. And this can improve even further compared to reverse annealing, but this method easily gets stuck in the local minimum. So it cannot cross this large energy barriers that we have for the spin glasses. And as you can see here, we end up in an energy that's relatively similar to the local search that we did with the learn-driven annealing. So just focusing on these quantum strategies with this iterative approach that we developed, this is the first time that we can actually solve these problems and yeah, get better results than just normal forward annealing. We then compared to classical solvers. Interestingly, here simulate annealing performed best. It was the only algorithm out of these that we tested that within the 24-hour time limit that we set was able to reach at least similar energies to our learning-driven annealing across the 10 random instances. Of course, the resources here depend on how much compute resources we use. So in this case, we used one node of our supercomputers, so 4 NVIDIA H100 GPUs and 4 Intel Xeon CPUs. But of course, if we would use more resources, this would accelerate the classical solver as well. So I wouldn't claim here any quantum advantage or whatever. But what I would say is that with learning annealing on the quantum annealer, we are now able to, the first time to actually compete with the classical solvers in both runtime and lowest energy. So these are the spin glass results. Another result that I want to share with you, quite recent result, is with prime number factorization. So here the idea is that we have an integer number n, we want to find the prime numbers a and b, and we can frame this as an optimization problem. We can formulate this in terms of a multiplication table and then put this on the chip. So this is the blue dots that you can see. These are the qubits that we use to solve this prime number factorization. Here on the right plot, you can see the results. This bottom plot shows you the optimization energy. So for this optimization problem, if we reach 0, this means that we find the correct prime numbers, a and b. And this top plot shows you the energy of the actual optimization problem that we put on the quantum computer. So if this is not 0, this means there are some errors in the multiplication table. Of course, we can find the solution to correct prime numbers while having some errors. You can see here with forward annealing, we cannot solve any problem. So even for the small 20-bit problem, we cannot find the prime numbers. But using iterative reverse annealing, we can at least solve problems up to 23 bits. We tried this then with our learn-driven annealing. You can see that we can also solve here up to 23 bits, but more importantly, we can also find the true ground state of the optimization problem, so no errors in the multiplication table. We didn't stop there. We tried then larger systems. You can see here the results for 23-bit, 25-bit, and 28-bit. So all the way to 28-bit, we can solve these instances and also find the true ground state. And to my knowledge, this is actually the new record for prime number factorization on the D-Wave, or at least with quantum annealing and this multiplication circuit strategy. And we are currently pushing this further with the Advantage 2 system to have larger system sizes. And this brings me to the conclusion, finally. So what I talked about today is learn-driven annealing. I introduced you to the idea of a feature Hamiltonian that allows us to guide the system through the instantaneous spectrum to overcome bottlenecks like phase transitions. This allows us to overcome hardware limitations such as short coherence times. And with this strategy, we can finally compete with classical solvers in both runtime and lowest energy. And with this, I'd like to thank you for your attention.
Thank you, Sebastian. I hope this talk has quenched your thirst for technical knowledge, but if it hasn't, we have more in today's schedule. I'd like to introduce you to Mayowa Ayodele. She's the Manager of Solutions Architect EMEA for D-Wave, and she's going to take the science closer to market, and she's going to give us some an overview of her work with D-Wave and how they are taking this technology closer to industry. Please welcome Mayowa to stage. No, you have the. Oh.
Thank you so much. Yeah. Thank you so much. Yeah, I'm Mayowa. I work with professional services. I work with a lot of clients, trying to create solutions. Today, I will be talking about how we compare our solution with the client solution. Can I have a slide up, please? I promise this is not going to be too technical. I try to stay away from something overly technical. So the aim here is to talk more about our experience with working in the industry. What are they comparing? compared to research papers where we are trying our best, for instance, in the quantum supremacy work that we did, we are trying to compare with the state-of-the-art classical solver, and this takes a lot of time for us to ensure that we can prove that quantum can, beyond reasonable doubt, give you a solution that is way better than classical. The kind of comparison we do with most clients are completely different. So I'll give a bit of background. Some of the things my colleague has already talked about before, our technology. I'll then talk about how we assess for technology fit. Is quantum annealing for everybody? Maybe not. I'll talk about the process of going from discovery, understanding whether it's even a fit at all, to going into production. I will then talk about how we measure success for most of our clients. And finally, I'll give an example of one of the client projects we worked on very recently, which is production scheduling for BASF. Okay, you may recognize this slide because my colleague had something similar. Again, we are the only quantum computing company that has both gate and annealing technology. I'll focus more on our annealing technology, but I want to highlight the fact that because there's always a lot of mixed messaging in the quantum industry. One, because most of our competitors are doing gate model. There's that concept of quantum is not ready today. Our quantum annealing solution is not only ready today, it's in production today. Okay, so yeah, we had this slide before. It was missing a few of the graphs. Just reiterating what my colleague said, our main secret ingredient in our hybrid solver is our quantum annealing. We have several other concepts. For instance, it talked to you about these special variables that we are able to use. And those are the kind of variables we've used in the use case I'm going to talk to you about today. So again, we're moving. It's very valuable I come from a research background. I had my PhD in operations research. And when we're comparing algorithms, we are focused on, are we able to outperform what is state of the art in terms of time to solution? Are we comparing on similar hardware? It's complicated when we're then talking about quantum. Does it make sense for you to compare on algorithms implemented on GPUs or CPUs? We're comparing, it's difficult to make an apples to apples comparison, right? But when we are dealing with most of our clients, it's not a case of we want to ensure that this is the only way the problem can be solved, or we want to compare against whatever is state of the art. Can it give us value? Can we have measurable outcome? Are we able to make more impactful decisions with this technology? Okay, so I'll talk briefly about how we assess technology readiness. Believe it or not, sometimes when we have certain use cases, we say to the clients, this is not the kind of use case we are good at. We are interested in succeeding. We want our clients to succeed. So we invest our time on use cases that we think our technology can solve properly. Optimization is the core of what we do. We do other things like AI and ML. And the reason we've focused a lot on this is because optimization problems exist in a lot of industries. It's just summed up into three things. We have certain choices we want to make, we have rules we want to follow, and we have something we want to minimize. Most companies have some sort of this problem in their business. Within the context of optimization problems, some of them are more complex than others. Some are simple enough, you don't need a quantum computer to solve it for you. So we focus on things that are considered complex, lots of interactions between different variables. For instance, you're talking about scheduling problems. The start time of one activity depends on the finish time of that activity. And all of these kind of problems can be quite complex. We're also talking about problems that are large. If it's small enough, maybe you can even calculate every possible
solution to that problem, and you don't need a quantum computer. Our technology thrives more because we're better able to take advantage of our quantum systems when the decisions are discrete. You have a finite number of choices that you can make. We've also done some work related to AI, ML, simulation. And my colleague talks about one of those in his presentation, which is what we have in our quantum supremacy work. We were able to simulate things that would have taken 1 million years in just about 20 minutes. We have also worked with clients on things like drug discovery, where we're able to use the quantum annealing directly to simulate structures that are more interesting for the client. Okay, once we've assessed the use case, now we know, okay, this is looking interesting. This might be one that is good for quantum. There are other factors we need to consider. One is there data? Do we have the data to be able to support that development? If we have the data, is it accurate? Is it realistic? Is it representative of what is going to happen in the future? So that when we build the model, we are sure that it's going to work when you then need to solve the problems going forward. Now, this is what the architecture looks like, where there are certain things that live on the customer's infrastructure, some other things that connect our hybrid solver. So our hybrid solver uses a range of resources, QPUs, CPUs, GPUs. We have my colleague talked about our Ocean platform before, where is the open source software you install on your system, you're able to build a model to be able to solve the problem. Now, my colleague also talked about how we define success, so I'll move to the value assessment piece. Okay, so once we've gotten to a point where we are able to say, okay, this is a good fit, we think this can, you can have some value from creating this solution. And a question that most stakeholders then have is, how do you compare the cost of implementing this solution versus the value you get from the solution? Sometimes the value is easy. It's like, okay, we're reducing distance, we can map that directly to a monetary value. So it's going to cost me X amount to install the solution, but the value I get is Y. Other times it's a lot more complicated because the value might be customer satisfaction, better customer satisfaction. You have a few more steps to get you to something tangible where you can then compare in monetary terms. So I'll talk about the process that we take for most of our customers going from discovery to production. Again, like I said before, we want to succeed as much as our clients. We want our clients to succeed, we want to succeed. So we are very intentional about our discovery process. Our discovery process is just, we are answering the question, should we even do this? Should we even bother? Is this a use case that would benefit from our quantum hybrid solution or our quantum annealing? Once we have determined that this is a sensible use case to do, we move over to the POT phase. The POT will typically take around 3 months. And here, we just want to know, is it actually possible? If we took a simple example, we tried our best, we created a solution for this, does it work? Are we able to get feasible solutions? Are the results even promising at all? And it's designed such that there are many validation points. So the gate one is that validation point where we're like, are we going to continue with this? Is this a sensible path for this particular problem? Once we move there, we move to the next phase where we are then incorporating all of the business rules, all of the constraints to ensure that that solution can be used in practice. Then we'd spend another 3 months just testing it out in practice to see how well it works. So I'll move very quickly to just an example. This is a use case we worked on very recently. It's BSF's production scheduling problem. The problem is one where we are trying to create a sequence of jobs. The jobs have due dates. We have tanks arriving at the facility across different dates. We want to create a sequence of small bottles on the small bottle filling line, a sequence of large bottles on the large bottle filling lines. There are many complexities here. When you switch from certain jobs, you have to completely wipe down the machine. You incur setup costs, etc. When you offload from the same tank across two filling lines, you need to start at exactly the same time. The tanks carry different kinds of products, so you want to ensure that you are filling the bottle with the right product. For this particular use case, we had 3 objectives. We want to minimize lateness. We want to ensure that orders are delivered on time. We want to minimize tank offloading time. We want to offload as quickly as possible. And we want to minimize setup time, so switching from different products. At the end of this project, we saw 14% reduction in lateness, 9% reduction in setup times, 18% reduction in tank unloading duration, which is massive. And the client was extremely happy with this. But most importantly, we got these better solutions with a much shorter runtime. It took 10 hours for the commercial classical solver they had. That was reduced to just 5 seconds. And what this means for the client is they can run multiple scenarios. Now, if a tank is going to be late, they can quickly run another solution without having to wait for 10 hours. So, key takeaways is we start with the right problem. We define success early. How are we going to be able to move this to production? How are we going to be able to convince the stakeholders that this is a valuable solution? And finally, we measure the impact in business terms. Thank you very much.
Thank you very much, Mayo. I think this has brought closer to home some of the work that Sebastian has been doing. Our third talk before lunch is our colleagues Eneko Saba. Eneko has been working on this field for many years. He did his PhD in classical optimization, finished in 2021, and he's a D-Wave research advocate. He's very much involved in all the international community that is taking these problems closer to, other researchers and also to industry. I also want to say before going for lunch that more people from the team has joined us and are sitting at the bottom of the room. So you want to talk to our team, they're over there. Don't be shy, please. And now, Eneko is going to tell us more about some of the real applications of his work and put it into context. So Eneko, please, the floor is yours. I'm so looking forward to hear from you.
Okay, hi all. Well, first of all, thanks as being part of the organization team. Thanks for being here. We are very happy of the great audience that we have. So I am talking about from science to industry, okay? How we work in TECNALIA in some low TRL research, and how we scale also these things that we make to the industry, okay? So I forgot this. I think that I will need it. But before, I know that you know that you are in TECNALIA, but I think that nobody had said nothing about TECNALIA. So I'm going to spend some minutes talking about TECNALIA, okay? We are one of the largest applied research centers in Europe, the biggest one, private research center in Spain. We are more than 1,500 people, and we work in more than 40 technologies. Of course, not all these people is working on quantum technologies. There's a quite big group in TECNALIA. I think that more or less 180 people working in digital transformation. in different kind of technologies such as computer vision, artificial intelligence, Internet of Things, and quantum computing and quantum sensing. So within the digital transformation group, there's quantum tech. Okay, we are more or less 30 people working in different areas of quantum technologies, okay? Because we work in quantum technologies. There are people working in quantum sensing, people working in quantum communications, and quantum computing, okay? And in quantum computing, there's people working in quantum machine learning, quantum simulation, and quantum optimization, okay? I'm going to talk about quantum optimization here. So, one of our biggest values, so why TECNALIA should talk about going from science to industry? Because we have a very good position between the academic world and the industrial world, okay? We sometimes act as a middleware between the universities in basic research or applied research projects, and also we work with companies in applied research projects and technological development. So we are in the middleware, so we know very well what is going from science to industry. Okay, so as in our department, we have different kind of objectives in the field of quantum optimization. Because we go from science to industry, we have our goals, more scientific goals, with low TRLs. We want to be key players on annealing control, design and implement our own methods to extract the best from the annealers. We want to design hybrid approaches that merge all these methods that we develop and fair benchmarking on this, of these methods. And also we have a more industrial, more high-level objectives in which we want to be key players on solving real-world use cases. We want to design complex hybrid pipelines, model and formulate real-world problems, and fairly benchmarking these methods that we develop. So I'm going to talk first about a couple of low TRL research that we made in the previous months. For example, we have published in last month one paper about embedding. If you don't know about what is embedding, I'm going to explain in very few words, no very technical, so sorry people from D-Wave, because this is not going to be very, very technical. So the embedding part is the part in which you take your problem, the problem that you have in your industry, and you map it in the quantum computer, because this is not straightforward, okay? You need to transform the variables of your problem, you need to embed into the qubits of the computer, okay? So this process is very complex, and to make this process, we need algorithms. So in this paper, we just demonstrate that the embedding is a crucial step for a good embedding, is a crucial step for obtaining a good performance of the algorithms that you are developing. Okay, so we provide a systematic experimental assessment of the mean or minor, which is the D-Wave algorithm that they use for make this embedding. And we published this paper in a very good journal, it's a Q1. But here, there's nothing industrial, okay? It's just academic, it's just science, okay? We have another one, which is on the transfer of knowledge in quantum algorithms. Transfer of knowledge is a field that in classical optimization has been studied many years, but not in quantum world, okay? Transfer optimization is that think about your industry, about your company. Sometimes, many times, you solve many similar problems every day. So why I don't use the knowledge of solving previous problems? Why I don't use this knowledge when I want to solve a similar problem? So we work on this in this paper, okay? One of the use cases is related with the reverse annealing of D-Wave, in which we demonstrate that we can, through this mechanism, reverse annealing, we can reuse solutions, previous solutions, to obtain a better performance. Again, we prove or we test this this mechanism, we make this paper with academic problems, the Trevisan problem, the NACSA problem. So there's nothing industrial here. But the main thing is that today, the community of quantum computing is evolving, is changing. The people is asking, okay, quantum computing, okay, very good, but for what? Okay, so the people wants to know which is the application of this new paradigm, okay? And for doing that, we need use cases. Of course, we need use cases, we need problems, we need data, and this is also something that we make in TECNALIA, okay? So, what do we need to successfully address a quantum use case? The first thing that we need, that sometimes is that we forgot about it, but it's very important, is a real industry partner. Many times we are talking about a quantum ecosystem, and we talk about academic partners, research centers, infrastructure providers, but sometimes we forget about industry, the companies. And these companies are crucial for evolving in a research topic, okay? So we need a real industry partner, which is sometimes is the missing key actor in the ecosystem. We need a commitment, a committed industrial partner with a real problem, with a need, or just a curiosity to know what they can make with quantum computing. Of course, access to real data, because the industry has the real data that make the problems real. Also, we need a certain level of digital maturity. Okay, the company should have a minimum level of digitalization. If they have an artificial intelligence method that solves their problem, okay, it's not a problem. Indeed, it is an advantage, okay? Because the quantum computing is not here to replace classical artificial intelligence or to replace the classical computing. It's here to work with classical computing. Okay, so we also need a suitable funding and collaboration framework because of the TRLs of the quantum world and the maturity of the technology. We need appropriate funding scheme aligned with this state of the technology, because we need long-term vision. Okay, we don't need just small use cases. We need a long-term vision to work with a company or to work with a partner for years. Okay, so which is the role of TECNALIA in all this chain? We want to translate the industrial problems that you have in your day-to-day operative, translate it into mathematical and quantum-ready models. We want to design and implement our own hybrid pipelines or use the ones that they will have. And something very important is to manage the expectations, risks, and technological maturity. This is very important because one of our main principles is that we aim to maximize the value in the first interaction with a client or with a partner, because we don't know if this first interaction is going to be the last one. So in order not to be the last one, we need to maximize the impact of the first interaction. So what do we need? What is very important to maximize the value in the first interaction? We need, and it's related what Mario has said, is a problem suited for hybrid quantum approaches or for quantum algorithms, okay? And which problem is a good candidate? Okay, this is not very technical, but this is something that maybe if you work in an enterprise, in a company, you don't know if your problem fills these characteristics, but in a couple of meetings, we are going to give an answer to this question. So if the decision variables of your problem are discrete, they are interconnected, there are specific rules and constraints that must be respected. For example, if you are working on a routing problem, one constraint is that you don't need to visit the same client 2 times, for example. Okay? The problem should be complex, so the search space must grow exponentially as the problem size increases, so the problem should be very, very complicated. The objective function should be light, for example, a mathematical formulation. In a routing problem, the objective function is just a mathematical formulation that measures the distance, for example, of a route. And current solutions, current classical solutions perform badly, just in time or in quality. This is if your problem fill all these points, so we have a good candidate for hybrid solvers. If we think in the ideal case in this NISC era that we are, in which the QPUs are not as mature as we want, these are the characteristics that are really favorable for a problem to be solved using quantum algorithms. All problem variables should be binary, quadratic constraints are either not required or easy to formulate, and the topology of the problem should fit well within the topology, okay? If the topology of your problem fits well with the topology of the computer, so the embedding, the thing that I talked earlier, is going to be easier, so the results are going to be better. But these problems does not exist today. You know, when in your company, you don't have this kind of problems. But it's not a problem for us, because we have the hybrid perspective, okay? The hybrid solvers, in which the classical computing and quantum computing work together, okay? Because from my perspective, and I think that also from the D-Wave and other perspective, the future is not going to be quantum, the future is going to be hybrid. It's going to be classical and quantum, okay? We need to build models, we need to build algorithms that join forces between the quantum computing world and classical computing world, such as the Strider solver or the sequence solver that already D-Wave have. So we can use this kind of hybrid algorithms to solve problems that are more complex or does not fit this kind of characteristics. But again, something very, very, very important is the problem qualification. It is a critical first step, just not to waste effort and realistic expectations, so to maximize the impact in the first interaction with a client or with a partner. So, okay, so how we solve a use case with a client or with a partner? We follow these points. Okay, first is the problem discovery and qualification, and in this part is where many ideas stop. But this is not this is a success. Here we discard the problems that are not. Sorry for the people that are taking photos because I am moving. Sorry. Many ideas here stop. It is a success because not every problem should move forward. Just the problems that are interesting. Okay. Of course, data and digital readiness assessment. We need to check with the partner, with the company, if they are digitalized enough to go forward. We need to model and formulate. We need to formulate the problem and model the algorithm that is going to solve the problem. We implement the problem, and we make a benchmark or a validation. Okay. Here, depending on the use case, we make a benchmark with a algorithm that a company has, or we just solve the problem and compare, or just have some discussions with the client. And then there's the industrial evaluation and realistic next steps. Here we decide if we scale, make more iterations, or it is just knowledge generation. And now I'm going to talk about very, very briefly, because the next session is going to be about use cases, okay, from science to industry. So 2 use cases. Okay, this is a use case that the D-Wave people know and I really like. Quantum Assist Path Planning for Robotic Quality Inspection in Industry 4.0. There's a lot of letters there, but the most important is that the problem here is the automatic generation of optimal robot inspection paths for complex parts under real operation constraints. So here in TECNALIA, we print this kind of pieces, okay? But when you print this kind of pieces, you need to make an inspection in order to know if the print has been is well printed, okay? So for doing that, we have a robot. It is this one. Everything, the robot is ours. The pieces have been, well, this is ours, it's mine. Well, not mine, it's from Estivalit. But everything has been made here. So the robot should take the piece and think that we can imagine that this piece has this piece has 100th of inspection points, so you need the robot to inspect all the points in order to know if the print is well. So this robot moving along the piece just to calculate or to check if everything is well is a trajectorial problem. It's a routing problem. And this routing problem we have solved with the Strider solver that the web has presented before. We made a benchmarking with 5 different pieces. This one. And we compare with classical state-of-the-art solvers. And the results are very good, okay? Are as good or very, are competitive in comparing with exact solvers, classical exact solvers, but in terms of time, is very, very, very fast, okay? So if you are more interested, bueno, you can take a photo, bueno, or you can just put D-Wave and EcoSaba in YouTube and you can see the video. And this is the last use case that Anton is going to talk about it later. It is very interesting. It's a quantum initialized warehouse optimization. The challenge here is that we have a large-scale warehouse storage optimization with complex constraints on space, stacking rules, and handling times. Perfecto. Anton is going to talk later about this. But a very interesting part of this use case is that Sericat already has an algorithm that solves this problem. So this is a case in which we think, okay, why we are going to build a new algorithm from scratch if they already have an algorithm? So we analyze the characteristics of the algorithm of Sericat, and we discovered that the initialization process was quite slow. So the main objective of this use case is not to solve the problem, the entire problem, but just to fill the gap of their algorithm. We just replace the initialization phase of their algorithm by an initialization phase using quantum computing, using the D-Wave annealer. And here, the results were very, very good, because in the same time that the classical initialization obtained few solutions, we can obtain hundreds with the same quality. Okay, this is a very, very interesting use case. If you are more interested, we make a patent of this model, and we make a materialization of this model using D-Wave. If you are interested, here are the links. So the main takeaways of this last part is that identifying the right use case is a major success factor. Hybrid is the default path. The future is going to be hybrid. It's not going to be classical. It's not going to be quantum. It's going to be hybrid. So we need both the classical and the quantum computing world working together. Benchmarking matters. We need to make a fair and rigorous benchmarking against classical solvers. And the industry is the key enabler. So real partners, real data, realistic expectations drive to meaningful impact. And that's it. Thank you very much.
Thank you. I mentioned before that watching him speak is like watching a rock star, you know, so it's good. Thank you so much, Aneko. But actually, it's a very good way to finish this part, because the science to industry in that last slide has summarized in 4 points, really the takeaway points for today. You know, the future is hybrid. You know, AI and quantum need to work together. Having a real problem is very, very important, and we cannot not have that. And fail early is success. Okay. Now we're only 5 minutes late. And I'm really pissed off because I cannot make jokes. You probably are hungry and want to go and have some food. Again, my colleagues are in the room. People from TECNALIA, people from the quantum team, please go and talk to them. And you know, we are here to answer any questions. And please talk to each other. You know, the people here and people at home, please go and have lunch. And we will be back in an hour. Thank you very much. ¿no? No, yo voy un intento. No, como ya un poco de fruta, pero bueno, Welcome back. Everybody awake? Happy? I hope we still have people on the other side of the camera. Okay. After the break, we have the perhaps most expected time of the day. We're going to talk about the use cases, 3 use cases that have been performed with the technology that we've been discussing today, and that are very down to earth. So you're going to see real results and hopefully take some ideas for your own work. I'd like to introduce Alma Ortuño, who is an innovation specialist in Telefónica, and she's been working on AI and quantum technologies for a few years now. She's performed quite a few tests. Alma is going to talk about a very specific problem, 3D beam packing, that is a project that we've done together with Worth, and we have here the boxes that are actually part of the problem. So she's going to be talking about what happens when you need to actually optimize the way things get put into these 3 boxes, which is a very tangible problem. Welcome, Alma, and we are looking forward to hear from what you say. Thank you.
Thank you. Good afternoon. My name is Alma Ortuño. I work in Telefónica, managing innovation projects. I would like to thank TECNALIA for inviting me to this important event in which the Waves is participating for the first time in Spain, I think, with its customers and partners, quantum computing, so thanks. In Telefónica, we have a very important strategy for working on quantum computing projects, such as the project with Worth. Telefónica is also the leading technology partner at Lantic and Vicaín Quantum Hub in Vizcaya. We manage the access to the platforms and to quantum computers in the hub. And we also work very closely with Lantic and the Provincial Council of Vizcaya, as it owns the hub and manage and leader the projects, the quantum projects in the hub. In this project, we are going to show you how quantum computing optimally solves the 3D beam packing for Worth. That is how the quantum algorithm determines the best way to place the items in the boxes. This is a problem that the quantum computer solves very well because it's a very a problem a problem that the quantum computing solves very well. We have the smallest box, the medium-sized box, and the biggest one that Worth uses. And thank you very much. And we have had the honor of working with Worth, that is a leading technology group in Europe, in Spain, for the sale of material to professionals. It's important to know that Worth is a very innovative company. So they have been delighted to co-innovate with Telefónica with this problem. And Worth currently uses a very good classical 3D beam packing algorithm. So it's a very high quality benchmark to beat. It's not difficult to overperform it. And so we are conducting a benchmark comparing the 3D beam packing algorithm quantum computing with the classical one made by Würth. So we are now, at this moment, we haven't finished all the tests yet. But we can say that approximately about 20% of all the orders will be optimized. And so Würth could reduce the total number of boxes and the volume to street KPIs. So it's very important for us. We have a very strong commitment to develop quantum optimization projects, such as this project that we have made in collaboration with TECNALIA and Centros. I'm very happy to have the first results in the project. Without any further delay, perhaps we can watch the video we have prepared for the event, in which we will show you the demo. So.
Every day, thousands of products move through logistics centers around the world. Different shapes, different sizes, different constraints, all needing to be packed, shipped, and delivered as efficiently as possible. For companies like Würth, a leading industrial supplier in Europe, this is not just a daily operation, it's a massive optimization challenge. Each order may include anything from small screws to bulky tools, and every item must be placed inside a box in the most efficient way possible. Now imagine scaling this to more than 1 million product references per year. Even with advanced classical systems, finding the optimal packing solution becomes incredibly complex. This is where quantum computing comes in. Telefonica, in partnership with Würth, is exploring how quantum technologies can transform logistics operations, starting with one key problem: 3D bin packing. The goal is simple: use fewer boxes, reduce empty space, and optimize every shipment. But achieving that goal is far from simple. Quantum computing allows us to explore many possible combinations at once, identifying more efficient packing strategies than traditional methods. And the impact is real. Fewer boxes mean lower transport costs, better use of space, and a more sustainable operation with less packaging material. Let's start the demo. We begin by logging into the platform, where we first authenticate ourselves to access the project's workspace. Once inside, we arrive at the main screen for the 3D bin packing use case developed for Würth. This project aims to optimize how items are placed inside shipping boxes. Let's take a look. Inside the platform, we access the 3D bin packing application developed for Würth. Here, every order becomes a problem to solve. When we compare the results, the difference becomes clear. The quantum solver is able to reduce the number of boxes and optimize the volume used more effectively than classical methods. We can also view all the jobs that have been launched so far, along with the option to submit new jobs to process specific Würth orders. Let's take a look at one of the jobs that has already been processed. Here we can clearly see how quantum computing yields more efficient results than the classical solver, both in terms of the number of boxes required and the street volume, which is the key metric for Würth. The results of this job, which processed a specific order, show us in the graph how the quantum solver running on the D-Wave computer yields a lower number of boxes for that order than the classical solver. These results directly translate to less transportation, less space, and lower costs. And this is not just numbers on a screen. We can actually see it. Through a 3D visualization, we compare how each solution arranges the items inside the boxes. We can observe how the quantum approach finds smarter ways to combine shapes and volumes. In some cases, what required 3 boxes with classical methods can now be solved using just 2. In others, even more efficient configurations are discovered. Each improvement may seem small on its own, but when applied to thousands of daily shipments, the impact becomes significant. We also can see a 3D representation of the order and how each solver has placed the boxes and items. We can visually compare the classical solution with the quantum solution and analyze exactly where each solver has placed each item: adhesives, tips, silicone, tools, and the rest of the catalog. This allows us to understand not only the numerical result, but also how it was obtained. Here we have the complete breakdown of the results obtained from quantum solvers and classical ones. We can analyze the total processing time, the quantum computing time, the final number of boxes, the volume used, and the processing cost. Additionally, the platform allows for direct benchmark-style comparisons between classical and quantum solvers for each order. We also have the option to run jobs exclusively on the quantum computer, much like how it would be done in a real production system. Let's see what happens with another order. In this second order, we also see how the quantum algorithm reduces the number of boxes to 1, compared to the 2 used by the classical algorithm. And finally, we will also examine the results for order number 3. In this example, we see the results of order 69, which is particularly interesting due to the wide variety of items it contains. Once again, we can see how the quantum solver better handles the combination of shapes, sizes, and volumes. And see how the quantum algorithm returns several possible optimal solutions. To conclude, the Q-Centroid platform provides a cost control view. On the Q-Centroid platform, we can gain full visibility into the tokens required to access quantum computing and the detailed quantum computing usage by each algorithm over time. Finally, the platform provides full visibility into performance and cost, allowing these solutions to be managed and scaled in real environments. This is more than a technological demonstration. It's a first step toward a new generation of logistics optimization, where quantum computing moves from theory into real business value.
This is the video, thank you. This is the video we presented at the Mobile World Congress. Thank you very much to Eneco, Irene, Carlos, that is here, I think. Carlos. Because of the collaboration. We are convinced, we have the conviction, we are going to achieve the quantum advantage in this project with the test we are going to execute in the next days. Thanks to the power of the waves advantage to do a quantum computer. And we share the results with all of us in a month, more or less. Our aim is to verify the powerful of the quantum computing. Yes. Thank you very much.
Results. You were asking for it. Okay, let's go to the next speaker. Let me introduce you to Anton Asla, who is the Innovation Director at Sericat, which is a company that has been working with us for a few years in the project that he's going to talk about. We've done quite a lot of work together. I think it's a very, very good example of the type of things Eneco was talking about in his last slide, finding a real problem, mixing, having a hybrid approach and trying to solve something and prove that things can be done. So thank you. Anton, the floor is yours.
To speak in Spanish, my English is so rusty. Bueno, yo os voy a contar cómo estamos explorando la... Esto quiero ir para atrás. El de abajo. Cómo estamos explorando la computación cuántica, que llevamos ya como unos 4 años, para resolver algunos problemas que se dan en el sector de la logística. Y sobre todo quiero contar 3 cosas. ¿Por qué empezamos a explorar la computación cuántica para resolver este tipo de problemas? Concretamente, qué problemas hemos abordado y cuáles han sido... pues cómo nos ha ido, ¿no? ¿Cuáles han sido los resultados? ¿Por qué? Bueno, yo trabajo en un grupo empresarial donde hay unas 30 empresas, la mayor parte de ellas operan en el sector de la logística, aunque yo estoy en el departamento, bueno, en la empresa de tecnología, en el departamento de innovación. Y ahí tenemos un sistema de vigilancia que nos alerta de si alguna tecnología que va apareciendo es capaz de resolver de una forma más eficiente problemas que tienen nuestros clientes o las propias empresas del grupo. Entonces ya hace unos años descubrimos cómo la computación cuántica prometía resolver de una forma más eficiente algunos problemas y en particular problemas de optimización combinatoria. Y se da la circunstancia de que en el sector de la logística, también en muchos otros, pero en el sector de la logística estos problemas son muy habituales. Yo os voy a contar ahora los 3 problemas que hemos abordado con computación cuántica, concretamente con Quantum Annealers, colaborando con TECNALIA y haciendo uso de las soluciones de D-Wave. El primero se parece mucho al que acaban de contar de Telefónica, es el problema del bin packing en 3D, pero nosotros lo hemos implementado para optimizar el número de contenedores marítimos que se necesitan para transportar una mercancía dada. Esto es un problema de optimización combinatoria porque las posibilidades de ordenar paquetes en contenedores crecen exponencialmente si crece el número de paquetes, incluso si crece el número de tipos de contenedores distintos que puede utilizar. Entonces, el objetivo de nuestro algoritmo era, dada una mercancía que está compuesta por paquetes de diferentes características, de diferentes dimensiones, pesos, capacidad de aguantar peso, etcétera, pues el algoritmo nos tiene que decir cuántos contenedores usar y cómo ordenar los paquetes en cada uno de esos contenedores, cómo hacer un poco el Tetrix. Y la cuestión es que una de las empresas de nuestro grupo pues nos puso una serie de restricciones que han hecho que el problema sea un problema real. ¿Qué restricciones son esas? Bueno, pues la primera de ellas es que yo no puedo colocar los paquetes de cualquier manera, porque si pongo los pesados en un extremo, él podría volcar. Entonces, tenemos que intentar conseguir que el centro de gravedad del contenedor cargado caiga en el centro de la base. Esto también lo utilizamos para camiones, con lo cual pasaría lo mismo. Si yo lleno un camión, el peso tiene que ir equilibrado en los 2 ejes donde van las ruedas. Luego, hay paquetes que no pueden soportar más de un peso, pues no los puedo poner debajo. Cualquier solución que me ponga el paquete debajo es una solución prohibida, entonces tienen que ir arriba del todo, ¿no? También puede suceder que parte de mi mercancía requiera un tipo de contenedor específico. Por ejemplo, puedo estar transportando mercancía congelada que tiene que ir en contenedores refrigerados. O puede suceder que tenga paquetes que tenga que entregar con mucha rapidez y los tengo que ordenar cerca de la puerta de apertura del contenedor para que cuando lleguen a su destino salgan en la primera remesa, ¿no? Incluso podría suceder que tenga paquetes que no puedan ir en el mismo contenedor por algún tipo de incompatibilidad. Imaginaros, pues no sé, productos químicos que pueden entrar en reacción, ¿vale? Este es el primer problema que abordamos con TECNALIA ya hace, pues no sé, empezamos como hace 3 años o 4 años. El segundo problema, que le llamamos Package Delivery, este es un problema que también tenemos en empresas del grupo. Nosotros tenemos empresas del grupo que todos los días se plantean la circunstancia de que están en su almacén y tienen que repartir mercancía por una zona geográfica y tienen que pasar por X puntos, ¿no? Y para ello tienen además una flota de camiones diferentes, de diferentes características, de diferentes costes, y alguien se pregunta, vale, ¿cómo planifico toda la entrega de hoy intentando que esa entrega tenga el menor coste posible? Vale, pues entonces en este caso lo que hemos hecho es un algoritmo que precisamente minimiza esa planificación de entrega de n paquetes que tienen que pasar por m puntos de geográficos. Esto concretamente es la zona de Mallorca, de Palma de Mallorca. Aquí tenemos depósitos y hay que hacer esas entregas. Y lo mismo, nuestras empresas transitarias nos pusieron pues, un conjunto de restricciones. Por ejemplo, Todas las rutas comienzan en nuestro depósito, el camión hace la ruta completa y vuelve al depósito y no pasa 2 veces por el mismo punto. Tenemos camiones dentro de esa flota que son propios y otros que son alquilados. Normalmente tendremos prioridad a usar los nuestros porque tienen un coste más bajos. También hay clientes que nos dicen, oye, tú tienes que pasar por aquí antes de tal hora, ¿no? Imaginaros, IKEA me dice, antes de las 12 tienes que entregarme la mercancía. Entonces, cualquier solución que pasara por IKEA más allá de las 12 sería una solución prohibida. Y finalmente, pues los conductores de los camiones no pueden conducir más de X horas al día. Entonces, pues este es el segundo problema que abordamos. Y el último de ellos, que tiene que ver con optimización de almacenes, es el que antes ha contado Eneco. Y en este caso nosotros tenemos empresas que tienen almacenes propios y que en esos almacenes almacenan productos de sus clientes, ¿vale? Porque tienen clientes que les llaman y les dicen, oye, mira, te voy a llevar mercancía, guárdamela en tu almacén y cuando yo te diga más adelante, preparas los pedidos con los artículos que yo te diga y los llevas al destino que yo te diga. Entonces, nosotros tenemos normalmente almacenes junto a los puertos y ahí se van almacenando los productos de nuestros clientes. Y como en los casos anteriores, pues aquí hay una serie de restricciones que sobre todo tienen que ver con cómo funcionan esos almacenes. Tenemos almacenes que normalmente los artículos se almacenan o en el suelo o en baldas. Hay artículos que pueden ir tanto en suelo como en baldas, pero hay otros que solo pueden ir en suelo. Además, hay artículos que se pueden apilar y otros que no. Y los que se pueden apilar, pues hay algún tipo de artículos que puedes hacer una altura de 7, otros de 15, etc. Entonces, ¿qué es lo que buscaba nuestro algoritmo? Es optimizar dos objetivos diferentes. Por un lado, la superficie de ocupación y por otro lado, el tiempo de manipulación de mercancías en el cual vas a tener que incurrir cuando tus clientes te pidan que saques esa mercancía. Entonces, llega el camión con mercancía y el algoritmo me tiene que decir dónde ubico esa mercancía para conseguir optimizar esos dos objetivos. Son dos objetivos que no se llevan bien porque si yo intento optimizar la superficie y apilo lo máximo que pueda los artículos que sean permitidos apilar, pues luego van a ser menos accesibles y me va a costar más tiempo preparar los pedidos a futuro. Y lo contrario, si estoy priorizando el hecho de optimizar el acceso a los productos del almacén, pues seguramente esté distribuyendo mucho por el suelo y no esté optimizando adecuadamente la superficie. Entonces, ¿qué es lo que hacemos? Pues dejamos que el operario, en un momento dado, decida qué peso le da a optimizar la superficie y qué peso le da a optimizar el tiempo. Si el almacén se está llenando, pues le va a dar mucha más peso, el 100% o el 80%, a optimizar la superficie y el resto a optimizar el tiempo. Y lo contrario, si tiene el almacén bastante vacío, le priorizará el optimizar el futuro tiempo de manipulación de los productos. Y como ha dicho antes Eneco, en este caso, aquí utilizamos el algoritmo, la computación cuántica para diseñar soluciones iniciales posibles a este problema dentro de estas restricciones, porque la computación cuántica nos posibilita generar muchísimas más soluciones en mucho menos tiempo que la computación clásica. Y de esta manera, pues generamos ese conjunto de soluciones iniciales, buscamos la más prometedora y a partir de ahí acabamos evolucionando con un algoritmo clásico para determinar dónde almacenamos esos productos que nos acaban de llegar. Y finalmente, ¿cómo nos ha ido? Bueno, pues hemos conseguido resolver contra todo pronóstico los 3 problemas. Y además con una calidad similar a la que conseguimos con algoritmos clásicos metaheurísticos diseñados para resolver específicamente cada uno de esos problemas. Es verdad que hemos conseguido resolver problemas de un tamaño pequeño. ¿A qué me refiero con un tamaño pequeño? Pues, por ejemplo, cuando hablamos del bin packing, pues del orden de 80 o 90 paquetes para ordenar dentro de los containers. Cuando hablamos del problema de rutas, pues pasando por 30-35 puntos máximo. Vale, pero en cualquier caso los hemos resuelto, pequeños, pero los hemos resuelto con calidad. Además, también hemos avanzado en el estado del arte de esas problemáticas, precisamente porque han sido problemas reales y sobre todo con la colaboración de TECNALIA hemos publicado sendos papers por cada uno de esos 3 problemas. ¿Y en qué estamos ahora? Pues estamos en varias cosas. Estamos en intentar resolver problemas mayores, en incorporar nuevas restricciones que nos ponen nuestras empresas, como por ejemplo cuando hagamos el package delivery, que es ese donde hacíamos el reparto por carretera pasado por N puntos, pues no solo vayamos repartiendo mercancía, sino llegado el caso vayamos también cogiendo mercancía cuando corresponda. Eso se llama la logística inversa. Y también no lo pone aquí, pero también estamos trabajando ahora con TECNALIA en la resolución de problemas de scheduling para la industria. Y esto es todo, amigos.
Thank you, Anton. Surprise, this was in Spanish, but on the version online, there were subtitles in English, so the people at home were able to follow this, and also the presentation was in English, so apologies for this. It was a last-minute surprise, but you know all the problems, so I'm sure you followed the discourse. Okay, this is our last talk, presenting results and how these technologies are being very useful for companies in their daily problems. And now we have, last but not least, Escolástico Sánchez, that is head of quantum at BBVA, and he's been working for a while in this type of problems. He's going to give an overview of what his team is doing, has been doing, and is going to do using this type of tech. So let's go. The floor is yours.
Thanks, Irene.
Thank you.
Wait, I don't deserve any applause till now. Wait a moment. I don't know if the presentation can be there. Hi, everybody. Thank you very much for your interest in our quantum journey at BBVA. Thanks, TECNALIA, Irene, Eneko, everybody here for this invitation. And if you allow me to see the presentation, I can say... Any problem with it? It was quantum encrypted. Maybe that's the problem. So I can tell you, because I'm in a hurry and I have to go very quickly here. My name is Escolástico Sánchez, Esco for you, and I am a mathematician that by chance started working in finance almost 30 years ago in the last century. And I began as a civil servant, as an inspector. Here we are. Thank you very much. As an inspector in the Spanish Securities and Exchange Commission. After that, I became a portfolio manager in BBVA Asset Management. And nowadays, I am leading the quantum effort, as Irene said, of our bank with a small but very powerful team completely devoted to this task. Okay. Next, please. This is what we are, BBVA, in figures. I'm not going to go through the figures, but beyond those figures, innovation is in our DNA. We think quantum is not just a promise. We think this is the next big thing. This is going to change the way we think, the way we calculate, and the way we compete. And us, as innovators, we don't want to stay behind the barriers. We want to lead this party, because there's going to be a party here. I'm going to send you 3 simple messages. First of them will be our quantum strategy, our two-phased quantum strategy. quantum safe on the one side, protecting clients, protecting infrastructure, protecting everything. And on the other side, quantum advantage, searching for advantage using this technology. This is going to be the part of the presentation, quantum advantage, not the other one. Second, I'm going to tell you what we have done with D-Wave. We have a long experience with D-Wave. I will tell you some of our main results and what we will do. This is the third part of the presentation with TECNALIA, with D-Wave, and related to these problems that we have. Let's talk about our strategy. Our ambition is to be an early adopter. For that, our mantra is move first, learn first, to win first. And to make that happen, we have built a strategy based on 3 pillars. Pillar 1, expertise. What is this? This is having smart people that can translate the problem of our business, of our lines of business, into quantum solvable equation. That is not easy. That is not easy at all, as Eneko said in his presentation. This is key. Second one, ecosystem. This is the part in which we make friends with startups, with universities, with technological partners, as TECNALIA, and with government, as the Vizcaya government, for example. And third part, these are the base of this triangle. The most important part is the third one, the height of the triangle, the execution. We focus on use cases that have impact in our bottom line, tangible impact in our bottom line. That is our main focus. Let's begin with expertise. Behold, this small team, but very mighty team, PhDs, mathematicians, physicists, practitioners, and academia experts. They got this mix with them. Second, let's move on to ecosystem. These are the main lines we are involved in. Quantum Safe Financial Forum, the event organization of Banks in Quantum Days with our friends of BQAIN and Atlantic. You know, our name is BBVA. 2 letters of the 4, for you that you don't know, are Bilbao and Vizcaya. The name of Bilbao and Vizcaya is everywhere, BBVA is. So it's like, sometimes this is a joke, it's like our father, the Vizcaya government, okay? And also we are working with the community of Madrid. She is our mother, okay? We are working with this type of things. And the part of execution, our main focus, our main energy comes to these use cases. And these are our flagship use cases. We deal with them with several technologies. First one, fraud detection. It's really important for a bank to detect the fraud, anti-money laundering, and all those type of things. What have we done? With quantum-inspired methods, have massive potential, and we have been able to detect more than 40% of use case of fraud in comparison with classic benchmarks. And we want to give a try to this same problem with Quantum Annealing. We want to give a chance to Quantum Annealing and D-Wave to solve this problem, and with TECNALIA. We'll see that in the third part of the presentation. Portfolio management. I know you are tired of portfolio management, but it's more or less the same problem that the BIM optimization that we have seen before. And Quantum Annealing excels solving this problem, especially when we put real constraint in the problem, like, for example, transaction fees. And the third one, derivatives pricing, the third use case that is our flagship. Here we have tried with Monte Carlo simulation, quantum Monte Carlo simulation, and quantum-inspired methods. You know, we are mixing this type, quantum-inspired from the one side, quantum annealing on the other, and lately, and eventually, quantum circuits. Let's go and see what we have done with D-Wave. BBVA have been collaborating with D-Wave, started the collaboration several years ago. Our first problem was dynamic portfolio optimization, this one that I was telling you about before, as I said. and well, promising results. Next, we try with feature selection in credit scoring and Forex arbitrage, again, with small problems, very good result, not to be in production, but very optimistic. The fourth use case that we did with them was QHRP. This is quantum hierarchical risk parity. This is a way of clustering assets, financial assets, with the same risk, more or less, in order to reduce the size of the portfolios. And last year, and as Alice here was with you last year, we finished a proof of concept with the initial use case, dynamic portfolio optimization. We tried to do the things better. So what are we doing? Testing, trying is the only way to become an early adopters. Last but not least, what will we do in the future? With you, with TECNALIA, and with D-Wave. Well, fraud detection, the first use case that I told you before. Fraud detection, and we want to try this new approach. This new approach with, Quantum Annealing, we have seen this morning, you have qubits, you have couplers. I'm a mathematician. For me, qubits, couplers, it seems perfectly with graphs, nodes, edges between nodes. So we are going to give a try to use or to detect in a better way fraud with your quantum annealing. And with the help of TECNALIA, we are going to try to identify communities, multiple communities, trying to do fraud in some way using this technology. Here we are. This is the project QMind that we are in with TECNALIA, and this is a project in which we mix the domain expertise that TECNALIA has, that you have. You have this expertise in quantum annealing and in this technology. We have the business expertise, detecting fraud pattern, because that is our main business. The main asset of a bank is the trust of the people. So we have to take care of that for sure. And 3 years of project under the Comunidad de Madrid, under the Madrid community, have funded the project. And that's what we are doing. And these are the 3 things that I wanted to tell you: the quantum strategy of BBVA, what have we done with D-Wave, and what will we do with TECNALIA and D-Wave. Thank you very much.
Thank you very much. Well, we are coming to almost the end of the session, and then I'm very happy that Javier made it through the door, because it's your turn, mate. Yeah, we're going to have a round table with the 2 startups that are working on this space, right? And are doing some really, very interesting stuff, not only with the D-Wave computing platform, but working in other parts of the ecosystem. And I'd like to introduce them in a way that I haven't introduced other speakers, because I want to tell you exactly how they portray themselves. I asked them to introduce themselves, and I will repeat it. And they did. So please welcome Carlos Kuczowski, CEO and co-founder of QCentroid. Carlos is a computing engineer by training with a deep passion for engineering the path from R&D to scalable software products. While others look at quantum as a future promise, Carlos focuses on making it usable for industry today. Carlos, please, one of the chairs. And we also have Javier González Conde, who is the CEO of Quantum Maths, a mathematician and a physicist, and a PhD in quantum physics. When the rest of us sees a terrifying equation, Javier sees a startup. Please, take the other chair. Thank you. Thank you. And I'm going to get a chair for me. Okay, so what was the first question? Well, we wanted to give you an overview of how we work in the ecosystem, because you've seen people from different institutions through the day. You've seen people that are doing cutting-edge research, and you've seen people that are working on the ecosystem and different parts of the ecosystem. And we want to give a voice to startups and people that are working in this space from a very different perspective. So these are people that do not control the technology. They are not building quantum computers. These are people that are playing with existing technology, that have seen an opportunity in the market and have bet their, professional lives on it. So what brought you to work in computing, quantum computing? What was your aha moment?
So to me, I was in academia. I was studying the PhD, and I saw the future in academia very gray or even black, because there was a lot of instability, lack of funding, and that was a technology like 6-7 years back that was not at all in the industry. So we saw a chance to do all of this transfer from academia to the industry, and to leverage a group of PhD students at the University of Basque Country to start with a company.
My sides come from the combination of getting fun, curiosity, and the business and market opportunity. So I had the privilege to lead an incredible team at BBVA, discovering new things. So as Esco was explaining, BBVA is one of the pioneers exploring quantum computing. So in this process, I was also playing with other technologies, but I'm an engineer, but I also love physics as an amateur. So I love quantum mechanics, and in the moment that I understand combining computer science, computer engineering with quantum mechanics, first is super cool. You can say to the people, I'm working on this. But the other part is we start seeing that there are a big gap between what is feasible and what the scientific people, as Javier and their team, know what is possible to do, what the waves are allowing to execute things, combining with what a corporation or a big organization or startups needs. So with this combination of fun curiosity, we saw that there is a big market opportunity to allow the wave system, as an example, with quantum maths and Javier algorithms, to be able to experiment with data in companies that we are seeing here. So this is our path.
Okay, thank you very much for that. That was one of those questions that it wasn't prepared, so they did good. Why to work with D-Wave? What are the type of advantages that you see to working with this platform?
Well, I will start first. Carlos. It's about the people. It's super easy to work with the Wave team from the beginning in different sites when I was, and now in Qcentric before incorporates. Second, from the technology point of view, is the easy to develop. So you need to understand for the quantum thing, but you need to have quantum, and later you need to put this in code that could be executable and also that you can update. And the way that the Wave structural the libraries and SDKs, that is more technical, is easy to work and to maintain and evolve. So this is something that other players in the industry are also working on, but I think that this part of the Wave is really easy to work. And later the results are also really good, and they are really interested to, as Alma from Telefónica and Eneco from TECNALIA was showing, the results are really, really, really interesting.
Thank you, Javier.
So to us, it's really attractive to work with D-Wave because several reasons. So first is the notion of you have quantum use cases where you have proven that it's possible to achieve certain advantage on certain businesses, and that's away from hype and like from claims that are like trying to say this can be much faster and this is my absolute no. The point is that land it, have use cases that are useful. So this is one first step. Second, I think that D-Wave has understood very well the notion of that Eneco was mentioning before of having hybrid solutions, because the solution is not going to be uniquely quantum. Quantum is not going to replace, it must be integrated. and our solution must be something complex in terms of how the different components of the solution must interact with each other. So in terms that the problem must be broken into pieces, and it's very complex to deal with all of these problems, and all the toolkit that has been developed around the QPU, I think this is a really high value. And also for us as developers, the SDK package of Ocean is amazing. And also having in mind that D-Wave is going to develop gate-based quantum computers that in the end are like the big promise that's going to be able to break all of the factorization prime problems like elliptic curves, etc. So it's like you have an eye on what can be done currently and have impact, but at the same time, you are going to provide the hardware for the future generation of computers. So I think all of this is very useful because you have both sides.
Thank you. And how does this tie to both your business models? Because you are providing some very specific and very different services to the emerging quantum community.
So our business model requires many things. We are going from consultancy projects where our customers want to explore, to benchmark, to see when it's convenient, to identify the problems, to identify formulations that are, let's say, more suitable for being solved with this. You have to educate the clients because not every problem can be solved with quantum advantage. Not every problem is suitable for this. And the next step, I think that is part of the challenge, is to leverage this, to extract KPIs, to leverage this as an engine for our solutions. So our solutions are not going to be purely quantum, are going to have more components, maybe AI, because an industry problem is not merely an optimization. It may include forecasting plus optimization plus something else. So this second part of integrating and leveraging all what we are doing is the next challenge for the future, to be able to provide something with standards, which is like the most difficult thing that we are facing today. So that's where we go.
So our business model, we at the beginning, we think that was easy to define because we decided that we don't want to create hardware. It's complex, it's extensive, and also between two of the founders, we have experience to create a hardware company 15 years ago. So we decided no more hardware. And we were thinking the opportunity of the platforms because the platform scales really well. Now the challenge is, and probably you are reading some of you in some articles, what is the platform games in the agentic era. So we need to evolve what is the business model. Mainly, we have our platform that is being used by different organizations to get access to hardware as the weight hardware, to be able to develop algorithms and to execute, and also being able to see what are the results from technical people and from business people. That is easy to say, but not so easy to develop. And now we decide to scale that we also need to make two things. Let people, human intelligence, to interact with our platform, also enhanced by quantum AI experts. So we put them a quantum expert to let them to make the thing faster. But also we start creating how the agents from our customer and partner need to interact with our systems. So now we are enjoying a lot how we allow agents to agents collaboration. Meanwhile, we define what is the evolution of the platform business model.
This is becoming a very serious conversation. It wasn't the intention anyway. Thank you very much. Those are very interesting answers. I dare to ask, why to work with a partner like TECNALIA? And don't tell me it's just for fun.
Well, I will start. Part of this is fun because it's fun to work with you. The second part, from a startup point of view, you need to have, you need to be competitive. You have at the beginning lack of talent, lack of capital. And working with RTO, this provides you talent and without the capital that you need, because you need to find angles, or you can find angles of collaboration. So TECNALIA for me is one of the top, well, for me, for all the people, the RTOs in Europe. And this allows us, being here in the region, to get access to this top talent. First, to be able to understand how we could collaborate in some R&D projects, to have our hands dirty. But second part for us is also impressive how we can be part of the engine, a small one, but we are looking to grow, of the R&D transition that RTOs need to do to the industry. This was a clear position from TECNALIA, how you need to be able to accelerate this transition through different actors, and startups are one of them. So for us, this is a big opportunity. The second, as we saw along the day, Telefónica, a big company working with you, when they call us, were super easy and fast to develop the partnership, to work together to make this use case, and also we're good. So, and without the TECNALIA, probably will not be able to have this level of excellence.
Thank you.
So for us, TECNALIA is one of the biggest RTOs in Europe, and that means that this is a very important bridge from academia to industry, and this knowledge transfer, and they go into very fundamental questions and as how to do the proper embedding for using D-Wave in the optimal way. So this is something really important that maybe there is no a need on the other side of the business, and someone has to do it, and we acquire this knowledge thanks to them. Apart from that, we have been collaborating, and having TECNALIA with us means that we have access to more technologies that are developed here, because quantum computing is one of them, but usually when you have to give solution to industrial problems, you have to combine, and you may need knowledge from different areas, from people who have been dedicating for the last 20 years to renewable energies and know more about the problems. So leveraging all of this is a really important thing. So knowledge of different industries and knowledge of how to combine our solution with solutions that are already in the portfolio of TECNALIA is very important. And I will say that also if you go to a client who is calling to your door to say, okay, this is a really interesting technology, yes, but having TECNALIA with us means that apart from being interesting, we turn it into something that they are going to go to have inside on premise, because TECNALIA is going to provide us with the trust, the capacity of testing, and it's going to validate that what we do is something useful. It's not the same as being like a startup of 10 people, rather than having TECNALIA working with us. So for the clients, is also a really important support to have someone that is verifying what we are doing and helping us a lot.
Thank you very much for those kind words, all true, by the way. Thank you. The challenges that you're finding in the quantum computing ecosystem to actually take your product, services, and ideas into the market. Challenges.
Well, maybe for this technology, for quantum computing, the main challenge is that we have unlocked a really small percentage of the potential of quantum computing so far, because we don't have the hardware, and we only have the tip of the iceberg, but there is still many more to be developed. And we need companies and corporations that, as some speakers mentioned before, that get involved into long-term adoption of this quantum computing. This is on one side, and on the other side, I will say that what we are seeing is that how to identify problems and how to check if those are suitable for quantum computing, and even knowing the problems is like something that when there is a lack of digitization, how do you want me to do algorithmization if you don't even have their digital assets ready? So I will say that it's complex because of these two reasons, and this is one of the main barriers, but so far there are like some achievements that can be done, and we go step by step following the development of this technology that potentially will be unlocked by the end of the decade.
So there are several challenges. I think that also we have here the privilege that we have one of the top ecosystem in quantum around the world. So we are seeing the things from going deep. So the complexity that we are seeing, others are only starting. I think that the challenges now that we are seeing and we are going to see is how we move from the early adopters that we have in this room, some corporations that at the end are some of the one that move the needle, how we move to the smart mover, or the later movers, how they start creating the attention, as Javier is saying. Quantum is creating utility, quantum is creating potentially advantage. We are seeing this utility and moving to advantage, but there are not so many companies that has this early mover vision and strategy. So we need to be sure that we are growing together the market, and we put the things as easy as possible, explaining with a concrete business impact, with the easy technology transformation, collaboration between us, the RTOs, the clusters here, to try to have a common message. So we need to miss to be fragmented. That I think that we are in a good position, but I think it's something that is key. The second challenge, and probably for me the biggest one, but also I think that is the biggest superpower that we have, are the agents and the AI. So when you work, the main thing is adoption. We have the technology, we have the algorithms, we have the science, the RTOs, but at the end we need the buyers. And now the buyers, when you go to a corporation, the main attention of the managing board, the board of directors now is how I need to move quick for adopting the agentic, whatever you want to call it, thing. So at the end, the numbers of hours that the people has in the managing board are limited. So they are talking so much on this that they cannot talk how they adopt quantum. So I think that this is a challenge that we need to work with, lead with, and also use. In the other side, the biggest acceleration that quantum could have is agentic, because this helps the people that don't understand quantum to make easy question fast, to move proof of concept that could spend, or could, yes, we spend 2, 3 years ago, 6 months, you can start making super fast, and you can start enhancing your team and your partners, putting other people to make dirty works like cleaning data, or no, but it's boring, but you need to do. All these things that maybe you need to spend days or weeks, now you can make in minutes or hours. So you can iterate and iterate, and you can convince for what quantum is useful. But as Javier is repeating, and also myself, is with this vision that need to be transformative, but we need to explain a really clear way what is the impact, and in combination with GPUs and in combination with assistants.
You mentioned the ecosystem. Thank you for that, because I think it is clear that we are in one of the top quantum ecosystems in the world. You both, anybody that follows you on LinkedIn, as anybody that follows you on LinkedIn, you can say that you travel globally and you move in very, very international markets, and you see a lot. What do you think is unique of this ecosystem we are immersed in? I think
that
answer.
For me, it's complex to explain for what is different and for what is unique. I think that I could explain for what is the uniqueness. First, I think that this was the ecosystem that started earlier. Became Basque, TECNALIA with the beta of quantum, you and us, I think started over 5-6 years. With this, the different corporates that started in other group, as Ametic in Spain, started 7 years ago. So we started having this conversation between industry, RTOs, and academia far away from other regions. So this creates this kind of competitive advantage. And in concrete in the region, I think that the work that we are building over giants, that we have the clusters here. We have a structure, as you were saying, Javier, with TECNALIA. It is not only about quantum, it's industrial use cases and expertise. We are building over all these ecosystem wires. So we are putting quantum at the top. Is that we don't need to create a new ecosystem words, we can use this. So I think that this is one of the unique things that we have here. And the other thing that we need to do is that we love to also export the things to outside. So we are creating this pipeline between external projects, as we have here the wave, and is why we are doing this in English, with internal team. And this creates a really good feedback loop, that creating things here, having the feedback from outside, and also coming back and in the other direction.
Yeah, so I totally agree with what Carlos said. I think that here we have been able to attract and gather, thanks to the brilliant work over years. We have hardware providers, we have companies dedicated to develop algorithms. We have companies dedicated to offering the platform to get the algorithms to known to attract clients in the industry. We have a really powerful industry traditionally because the history of Bilbao. And I think that we have a lot of momentum we have this brilliant era of access to as many hardware providers as possible, probably the place where more access in the world. And we have a lot of our industry engaged doing proof of concepts with the companies. So I think that now the point is to keep the momentum. That is not something easy, because when you do something great, to keep it going becomes harder and harder. But I know that this, even though this is hard, this is a model, and we have been able to achieve something probably pioneer in the world. So now we are able to produce like full stack chains. Like we have Carlos' company, my company, and maybe hardware providers, and we can go as a team to sell to other markets, other hubs. So the world is very large, and I think that we are creating a model that is going to be the reference, and that people worldwide are going to look at it. Companies will want to come and to set up a subsidiary in Bilbao and to invest in Bilbao because the initiative that we have. So I think that there's a lot to come, but also we have to be careful with the expectations, managing the expectations, because that's something that is complicated when you are doing such a great thing.
Well, actually, one of the mottos of this conference was honesty and practicality. So taking these things closer to industry with those values in mind. If I was the three wise kings, what would be the wish you would ask for 2026?
That's tough. That was not in the list, sir. So now I need to think. So as we have said, we are establishing collaborations. We have a collaboration ongoing with TECNALIA. We are collaborating also with Carlos. So we would like that this year becomes the first year where we are able to do the first export in terms of what we have cooked here can be presented in other markets. Could be like Southeast Asia, could be Middle East, could be America. But in the end, that we are something that we create something that can go beyond frontiers and can be into different markets, and that actually the brand that we have created here is expanded worldwide.
I agree. You put me easy in this way. Because I was thinking more GPUs, more QPUs, more corporates, more SMEs.
More funding.
Yes, but the funding, when you have computing and you have corporates, the funding comes because it's super practical. So you don't need to start explaining for what quantum you put. I have this number of customers, and later is when you need to explain what you are doing after signing, when you show the customers. But without joking, I think what Javier said is really bold, and we need to believe what we are saying and also visualize. I think that the vision, and is you say, okay, what I will be happy to celebrate 1 year from now, that we will have here at least other 4 hubs, international one, maybe Asia, Middle East, maybe America, and being the reference here, how we help them to be hubs and how we create here a gravity of half of hubs. So how we share our best practices to them, meanwhile we learn what we can take from them and what we can offer to them. I think that this will help us to grow a lot. We'll have to have this fresh talent, moving hardware companies, and I think that exporting what we have, meanwhile learning what the other have.
Those are very difficult wishes. I will see if I can grant them to you, but if I can, I will.
I will put these 4 KPIs, 4 more hubs for the next year.
Thank you so much for coming today. Thank you very much.
Thank you.
So we're coming to the end of the day. We're going to close the day. Hopefully you will be able to come back home and with some new insights and some ideas for you and your businesses, and maybe something to discuss with your friends. I don't know if your friends get glassy eyes when you talk to them about what you do for work. Mine definitely do. But I hope you have learned something very, very useful today. 1, 2, 3, or 4 things. We have 2 amazing people to close the day. So it's not going to be me. It's going to be our Director for Digital, Josep Alaka, and Andrew Bithell. What was your regional sales manager of D-Wave, our top D-Wave representative here? So, one for you.
Thank you.
So we have to improvise. First.
Yeah, well, I just want to say a big thanks to everybody. It's been such a fantastic day. One of the things that we don't get to see very often doing the jobs that we do is all the success that comes back off the back of the technology. And I'm absolutely amazed by the ecosystem you've got going here. It's absolutely fantastic. You should be really proud of everything that you're doing. And it's really, from our perspective, it's really great to see the application of some of the technology in the real world.
And again, thank you to D-Wave and all the attendees, both physically here and online. I have been taking some notes during the day, and I just wanted to close with a few ideas, trying to summarize some of the things that have been said. I would say that we have, in the one hand, we have many challenges, and we are aware of the challenges that we have ahead. But in the other side, we have huge opportunities. I will try to summarize many of the things that have been said today. I think that we all are aware that there is a lot of hype around quantum computing, both annealing, both gate-based, whatever. There is a huge hype. Hype is risky because it creates expectations that are not met by reality, not yet. Then we have the problem of translation, because sometimes we get lost in translation, as in the movie, because we can't translate a real problem to somehow a solution that can be achieved. Then we have the problem of talent, that we have very few people. How many people are we here? Well, maybe 6 years, it could have been, I don't know, 6, 7 people. Today, 30, 40 here, I don't know how many online. Hopefully in the coming years there will be hundreds here. Then we have also the issue of not being the first proof of concept, the last one, related with hype. And then also we have mentioned the problem of research and funding, because there is plenty to be done yet. You have said most of the use cases, they are papers. So papers are related with academia, but actually we're talking about papers, about applications, about real applications. So we have this barrier of research, of funding, this death valley of research. But on the other side, on opportunities, Sebastian, I have really liked your presentation. I mean, this learning-driven annealing, it goes to one of the key topics, that is not being stuck in suboptimal solutions, and it's key for any annealing process. So I think that we are in a world of science, technology, open, and going to opportunities. There is a track record. We have seen here many examples. You could say that some are still experimental, some are somehow in production, somehow are not, but many of them are already in production. So D-Wave, born in 1999, so last century company. So, I mean, there is a track record. This is not something that started yesterday. Then we know that we are dealing with problems that are very relevant to the economy, very relevant in terms of euros, in terms of saving some costs, in terms of logistics, in terms of many things. So these problems are really about the euros, about dollars. They are really meaningful. Pounds, I would say. The technology is here today. You are presenting Advantage 2, Leap, Ocean, Stride, technologies that we all use here in TECNALIA and in the partners. You have presented technologies of tomorrow, Advantage 3, this acquisition you have done of the gate model, etc. So we see that plenty is coming ahead. And then last but not least, we have the ecosystem. We have the clusters, we have the initiatives from the Biscay government, the Basque government. We have companies, we have partnerships. And we have had some pinchos and some drinks and some chit-chatting out there. So I think that this part, the human part, the ecosystem part is very important. I'm sure that some of you here physically, sorry for the people online, is the first time that you have seen each other. So I hope that this creates a community, and in the coming years, we build on trust, we build more use cases and more quantum applications. Thank you.
Thank you very much.
Thank you so much. Okay, I'm back. Right. Well, thank you very much. This is the end of the day. I hope you've learned a few things or two. I've said that before. I hope we all go back home with a good feeling about having met the teams from D-Wave, from TECNALIA, from the different companies that have had a presence today. And I just want to say, you've been a wonderful audience. This is TECNALIA. Thanks and goodbye.